Imagine a universe so vast it contains billions of galaxies, each with countless stars and planets, and we've only just begun to uncover its mysteries. From the birth of stars to the dance of planets, the cosmos invites us to explore our origins and our place in it. Join us as we delve into the stories of evolution, consciousness, and humanity's journey as stewards of Earth and explorers of the stars. The origin of the universe has intrigued scientists and thinkers for centuries. Among the most prominent theories is the Big Bang theory, which proposes that the universe began as an extremely hot and dense point around 13.8 billion years ago. According to this theory, the universe has been expanding ever since. Evidence supporting this idea includes the cosmic microwave background radiation, which is the afterglow of the initial explosion, and the observed redshift of distant galaxies, indicating they are moving away from us. Another significant theory is the inflationary model, which refines the Big Bang concept by suggesting a brief period of rapid expansion occurred just after the initial explosion. This inflationary phase would have smoothed out any irregularities in the early universe, explaining why the universe appears so homogeneous on large scales today. Scientists have developed these ideas further by exploring various mechanisms that could have driven this rapid expansion, and while much remains uncertain, this theory provides strong insights into the conditions that prevailed at the universe's birth. Additionally, there are theories surrounding multiverses, suggesting that our universe might just be one of many, each potentially having different physical laws. This notion challenges our traditional understanding and raises profound questions about the nature of reality itself. If true, this could mean that what we perceive as the universe is just a tiny slice of a much larger, possibly infinite collection of universes where everything we understand is but one variation within a grander tapestry. Lastly, while these scientific theories are widely accepted, philosophical and theological perspectives about the universe's origins also coexist. The beauty of this topic lies in its complexity, drawing connections between physics, cosmology, and even metaphysics. As our understanding deepens with new discoveries and technologies, the quest to comprehend our universe's beginnings continues to flourish, inviting endless curiosity and exploration. The Big Bang theory serves as the prevailing explanation for the origin and evolution of our universe. According to this theory, everything we see today began as an incredibly hot and dense singularity approximately 13.8 billion years ago. At that moment, there was no space, no time, and no matter. Instead, the entire universe was packed into a single, infinitesimally small point. Then, this singularity underwent an explosive expansion known as the Big Bang. This expansion was not an explosion in the conventional sense, but rather a stretching of space itself, which catalyzed the formation of the fundamental forces of nature and all matter. As the universe expanded, it cooled down, allowing protons and neutrons to form. A few minutes after the Big Bang, these particles began to combine into the simplest elements, primarily hydrogen and helium. Over millions of years, these elements came together under the force of gravity, leading to the formation of stars and galaxies. Initially, the universe was a dark and empty expanse, characterized by vast clouds of gas and dust. But as stars ignited and began their life cycles, they created heavier elements, contributing to the cosmic material from which planets, galaxies, and ultimately life on Earth would emerge. Through the observation of cosmic background radiation and the movement of galaxies, scientists provide substantial evidence in support of this theory. The background radiation serves as a remnant from the early universe, revealing clues about its hot and dense origin, while the current expansion of galaxies illustrates how space continues to grow, a dynamic reminder of the universe's explosive beginnings. The Big Bang theory not only describes how the universe began, but also how it continues to evolve today, inviting us to ponder the vastness of time and the mysteries that lie beyond our reach. The Big Bang theory, which proposes that our universe began as an incredibly hot and dense point approximately 13 billion years ago, is supported by several compelling pieces of evidence. One of the most significant is the observed expansion of the universe. When astronomers study distant galaxies, they find that they are moving away from us, and the farther away a galaxy is, the faster it appears to be receding. This discovery, made by Edwin Hubble in the early 20th century, suggests that the universe is still expanding, a phenomenon that aligns perfectly with the idea of an initial explosive event. Another strong piece of evidence is the detection of cosmic microwave background radiation. This faint glow permeates our universe, providing a snapshot of the universe as it was just about 300,000 years after the Big Bang. Scientists discovered this radiation in the 1960s, and its uniformity and spectrum closely match what would be expected from a hot, dense early state. The existence of this relic radiation serves as a powerful confirmation of the Big Bang theory, as it supports the idea that the universe has been cooling and expanding since its inception. Furthermore, we observe the abundance of light elements such as hydrogen, helium, and lithium in the universe, which also fits neatly with predictions made by the Big Bang model. According to the theory, these elements were formed in the first few minutes after the Big Bang during a period known as Big Bang nucleosynthesis. The proportions of these elements that we observe in the cosmos today align with what the theory suggests should be present, providing further validation. Finally, advances in technology have allowed scientists to gather evidence from the structure of the universe on a grand scale. By exploring the distribution of galaxies and galaxy clusters, researchers find patterns that indicate the influence of dark matter and the initial conditions of the universe. These observations complement the Big Bang model and provide a coherent framework. Together, these compelling lines of evidence create a robust case for the Big Bang theory, revealing a universe that is dynamic, evolving, and steeped in history. The early moments of the universe's existence, often referred to as the first few minutes after the Big Bang, hold profound mysteries that continue to intrigue scientists and cosmologists. One of the most tantalizing questions pertains to the exact nature of the Big Bang itself. We understand that the universe began as an extremely hot and dense point, but what caused this initial expansion? This moment remains shrouded in ambiguity, leading researchers to explore concepts like quantum fluctuations that might have triggered the inflationary expansion. Another significant enigma is the nature of dark matter and dark energy, which together make up about 95% of the universe. We know little about what dark matter is, though it seems to exert gravitational forces on visible matter, shaping galaxies and galaxy clusters. Dark energy, on the other hand, is responsible for the accelerated expansion of the universe, but its properties and origins remain elusive. Understanding these phenomena could potentially unlock the secrets of our universe's early dynamics. Additionally, the conditions during the first moments of the universe are a subject of great speculation. Scientists have theories about how elements like hydrogen and helium formed just a few minutes after the Big Bang. However, the detailed processes and interactions that occurred during nucleosynthesis are still not fully understood. Researchers are continually working to improve their understanding of these fundamental processes, which set the stage for the formation of stars and galaxies billions of years later. Finally, the concept of cosmic inflation introduces another layer of complexity. This theory posits that, in the tiniest fraction of a second after the Big Bang, the universe expanded exponentially. While it offers a solution to certain puzzles regarding the large-scale structure of the universe, The specifics of what drove this inflation and how it fits in with our understanding of particle physics are still open to exploration. With each new discovery, we move closer to deciphering these mysteries while marveling at the intricate tapestry of our universe's early history. Scientists study cosmic microwave background radiation, often referred to as CMB, to unravel the mysteries of the universe's origins. This faint glow permeates every corner of space and is a relic from the early universe, specifically from when it cooled enough for atoms to form about 380,000 years after the Big Bang. As the universe expanded, this radiation stretched and cooled, allowing researchers to capture and analyze it using highly sensitive instruments. To study CMB, scientists employ a variety of sophisticated telescopes and satellites. One of the most notable tools was NASA's Wilkinson Microwave Anisotropy Probe, launched in 2001. This satellite mapped tiny fluctuations in temperature and polarization of the CMB across the sky. The detailed information gathered allows scientists to examine variations in density from the early universe, essentially providing a snapshot of these primordial conditions. Data from such observations helps refine our understanding of cosmic expansion and the structure of the universe. What researchers have learned from CMB studies has transformed our understanding of cosmology. The temperature variations correspond to regions of matter density, leading to insights into the formation of galaxies and large-scale structures. In addition, the CMB carries clues about the composition of the universe, revealing a surprising balance between ordinary matter, and dark energy. Current estimates suggest that only about 5% of the universe is composed of atoms that make up stars, planets, and living beings. The rest is largely made up of dark energy and dark matter, components that continue to intrigue and baffle scientists. Moreover, the CMB has provided evidence for theories such as inflation, which posits that the universe underwent rapid expansion immediately after the Big Bang. Observations have shown a remarkably uniform background, supporting these groundbreaking ideas about the universe's early moments. As scientists continue to analyze CMB data, new technologies promise even more profound insights, challenging our understanding of the cosmos and revealing even more about its vast, enigmatic nature. The question of what existed before the Big Bang remains one of the most profound mysteries in modern cosmology. The Big Bang marks the moment our universe began expanding, which occurred approximately 13.8 billion years ago. However, our understanding of time and space begins with this event, making it difficult to conceptualize what, if anything, preceded it. One intriguing idea is that the Big Bang may not have been the absolute beginning, but rather a transition from another state of existence. Some cosmologists suggest models such as the cyclic universe theory, which posits that the universe undergoes endless cycles of expansion and contraction. In this scenario, the universe may have collapsed into a singularity, only to emerge again in a new Big Bang. Another possibility is framed by certain interpretations of quantum physics, where space and time could behave differently at extreme scales. The concept that time may not exist in the manner we understand it prior to the Big Bang prompts us to reconsider not just the nature of the universe, but also the very fabric of reality itself. The question challenges our intuitive perceptions, suggesting that conventional notions of before may not even apply. Ultimately, while we have fascinating theories and models, we currently lack definitive evidence to ascertain what, if anything, existed before the Big Bang. Ongoing research and future discoveries in cosmology and physics may one day illuminate this enigmatic period, further transforming our comprehension of the universe and our place within it. The quest for answers continues to captivate scientists and enthusiasts alike, driving exploration beyond the edges of the known cosmos. The formation of galaxies is a fascinating journey that begins in the chaotic universe shortly after the Big Bang. Initially, the universe was a hot, dense state, filled with particles and radiation. As it expanded and cooled, slight variations in density across space allowed regions to begin clumping together. These clumps of matter, composed primarily of hydrogen and helium, served as the seeds for galaxies. Over millions of years, gravitational forces caused these clumps to merge and grow larger, eventually forming the first galaxies. As galaxies developed, they gravitated toward each other, influenced by their shared gravity. This interaction led to an array of galaxy types, including spirals, ellipticals, and irregular shapes. Spiral galaxies, like our Milky Way, are characterized by their well-defined arms winding around a central bulge. In contrast, elliptical galaxies have a smoother, more rounded appearance, lacking the distinct structure of spirals. Each type of galaxy plays a critical role in the evolution of the cosmos, harboring stars, gas, dust, and dark matter in a delicate balance. Galaxies are not just clusters of stars. They are key players in the universe's larger narrative. They are the primary sites where stars are born, evolve, and die, recycling their materials back into the interstellar medium. This process enriches the cosmic environment with heavier elements necessary for the formation of planets and the emergence of life. Moreover, galaxies interact with and influence one another through gravitational forces, leading to phenomena such as collisions and mergers, ultimately reshaping the structure of the universe. The role of galaxies extends beyond their individual components. They serve as laboratories for astrophysical processes and a canvas for understanding the universe's history. The study of galaxies informs scientists about dark matter, the expansion of the universe, and the formation of large-scale structures. Galaxies are the fundamental building blocks of the cosmos, offering us a glimpse into the past and insights into the universe's future. Each galaxy is a chapter in the cosmic story, inviting us to explore the mysteries of our existence and the vastness of the universe. Dark matter and dark energy are two of the most enigmatic components of our universe, making up a staggering 95% of its total mass energy content. To put this in perspective, visible matter, like stars, planets, and galaxies, constitutes only about 5%. This stark disparity leads scientists to probe deeper into the nature of these elusive entities. Dark matter is a form of matter that doesn't emit, absorb, or reflect light, making it impossible to detect directly with telescopes. Its existence is inferred through its gravitational effects on visible matter. For instance, galaxies spin at such speeds that, without the gravitational pull of dark matter, they would tear themselves apart. This unseen mass is thought to anchor galaxies together and is believed to be spread throughout the universe, influencing its structure on a cosmic scale. Despite extensive research, scientists have yet to identify the precise particles that make up dark matter, although candidates like weakly interacting massive particles, or WIMPs, have been proposed. On the other hand, dark energy is an even more baffling aspect of our universe. It is a force that is driving the accelerated expansion of the universe. While gravity pulls objects together, dark energy acts in opposition, pushing galaxies apart. This has profound implications for the fate of the cosmos. If dark energy continues to dominate, it suggests a future where galaxies drift ever further away from each other, leading to a cold, diffuse universe. The mysteries surrounding dark matter and dark energy are not merely scientific puzzles. They challenge our fundamental understanding of physics. What distinguishes them from ordinary matter is not only their invisibility, but also the ways they defy our traditional assumptions about how the universe works. As researchers continue to seek clues and evidence, the potential for groundbreaking discoveries looms on the horizon, promising to enrich our understanding of the universe and our place within it. Black holes are perhaps one of the most enigmatic and fascinating components of our universe. Their role in the cosmic environment is profound, influencing not just their immediate surroundings, but much of the structure of galaxies and the behavior of celestial bodies. These cosmic giants possess an intense gravitational pull that can affect the orbits of stars and the movement of gas and dust, shaping the very fabric of the cosmos. The formation of a black hole typically begins with a massive star. When such a star exhausts its nuclear fuel, it undergoes a dramatic transformation. The core collapses under its own gravity, while the outer layers are expelled in a violent explosion known as a supernova. This spectacular event leaves behind a core so dense that not even light can escape its gravitational grip, creating what we call a black hole. There are various types of black holes, with stellar black holes, formed from individual massive stars being the most common. However, there are also supermassive black holes which lurk at the centers of galaxies, including our own Milky Way. These supermassive black holes can be millions or even billions of times the mass of the Sun. Current theories suggest they formed through the gradual merging of smaller black holes and the accretion of massive amounts of gas and dust over billions of years. Black holes also play a critical role in galaxy formation and evolution. The presence of a supermassive black hole can influence star formation rates and the distribution of matter in a galaxy. They can emit powerful jets of energy that affect surrounding gas clouds, often triggering new star formation in regions that might otherwise be dormant. Thus, black holes are not just cosmic vacuum cleaners. They are vital players in the grand narrative of the universe, helping to shape the stars and galaxies we see today. Neutron stars present one of the most fascinating and perplexing challenges to our understanding of the laws of physics. These celestial objects are the dense remnants of massive stars that have undergone supernova explosions. A neutron star packs a mass greater than that of the Sun into a sphere only about 15 miles in diameter. This extraordinary density means that a single sugar cube-sized amount of neutron star material would weigh as much as all of humanity combined. This situation pushes the limits of our knowledge in ways that few other phenomena can. One of the most intriguing aspects of neutron stars is their composition. They primarily consist of neutrons, which are subatomic particles without an electric charge. The conditions inside a neutron star are so intense that protons and electrons combine to form neutrons. The question of how matter behaves under such extreme conditions is a key aspect of modern physics, as our current theories do not adequately describe the matter at these densities. The behavior of particles in this ultra-dense environment challenges the foundations of quantum mechanics and our understanding of nuclear physics. Another fascinating characteristic of neutron stars is their incredible magnetic fields, which can be 1 trillion times stronger than Earth's magnetic field. Some neutron stars emit beams of radiation from their magnetic poles, leading to the phenomenon known as pulsars. These stars spin rapidly, and as they do, they sweep these beams across space. The study of pulsars not only helps us understand the life cycle of stars, but also plays a crucial role in testing theories of gravity and the fabric of space-time itself. Moreover, neutron stars are laboratories for investigating extreme states of matter, which might even help physicists unlock mysteries about dark matter. The interactions and pressures occurring inside neutron stars push known physics to its edges, presenting unique opportunities for research. As we probe deeper into these enigmatic objects, we find ourselves facing profound questions about the fundamental nature of reality and the forces that govern the universe. Each new discovery could revolutionize our understanding, reminding us how much we still have to learn about the cosmos. Massive cosmic events, such as supernovae, play a crucial role in the life cycle of stars, acting like cosmic recycling processes. When a massive star reaches the end of its life, it can explode in a brilliant burst of energy, a supernova. This moment is not just spectacular, it marks the transformation of the star and the dispersal of its elements across the universe. The explosion of a supernova results in an array of elements being released into space. These elements are forged within the star during its lifetime, especially in its core. For example, as a star goes through nuclear fusion, it creates heavier elements like carbon, oxygen, and iron. When the supernova occurs, these elements are expelled into the surrounding interstellar medium. This enriches the cosmos with the building blocks necessary for the formation of new stars, planets, and eventually life itself. Moreover, supernovae also influence the dynamics of their surroundings. The shock waves produced during the explosion can trigger the collapse of nearby gas clouds, initiating the formation of new stars. This process illustrates a beautiful cycle of rebirth in the universe, showcasing how the death of one star can lead to the birth of many others. In this way, supernovae are essential to the ongoing evolution of galaxies, as they enhance the chemical diversity and influence star formation processes. Additionally, the remnants of the supernova, often forming nebulae, can become regions rich in new star formation. These nebulae are clusters of gas and dust, a fertile ground where gravity can pull material together, eventually sparking the process of star birth all over again. Thus, massive cosmic events like supernovae not only signify the end of a star, but also herald the beginning of new cosmic entities, emphasizing the intricate interconnectedness of the universe. Gravitational waves, first predicted by Albert Einstein over a century ago, have transformed our understanding of the universe since their first detection in 2015. These ripples in space-time, produced by massive cosmic events such as colliding black holes or merging neutron stars, offer a groundbreaking way to observe the cosmos. Rather than relying solely on light, gravitational waves provide a new sense of hearing, allowing us to detect and study phenomena that were previously invisible to traditional telescopes. One of the most remarkable insights from gravitational wave observations is the existence of black hole mergers. When two black holes spiral inward and eventually collide, they send out powerful gravitational waves that can be picked up by detectors like LIGO and Virgo. These observations have confirmed that black holes can coalesce, creating even larger black holes. This discovery not only supports existing theories, but also opens up questions about the population of black holes and their formation processes throughout cosmic history. Furthermore, the detection of gravitational waves from neutron star collisions has revealed astonishing information regarding the origins of heavy elements in the universe. In 2017, when astronomers observed such an event, they also found traces of gold, platinum, and other metals dispersed in space. This supports the idea that these cataclysmic events are key sites for nucleosynthesis, the process through which heavy elements are formed, transforming our understanding of where many of these precious materials come from. The study of gravitational waves is ushering in a new era of astronomy, one that complements the electromagnetic spectrum. As we continue to observe and analyze these cosmic phenomena, we will sharpen our understanding of fundamental questions related to the nature of gravity, the fabric of space-time, and the very evolution of the universe itself. Gravitational wave astronomy holds the promise of uncovering mysteries that have long eluded scientists, making it an exciting frontier in the quest to understand the cosmos. The theory of relativity, proposed by Albert Einstein in the early 20th century, revolutionized our understanding of space and time. Traditionally, we viewed space as a vast void in which events occur and time as a constant tick-tocking away uniformly. However, Einstein introduced the concept that space and time are intertwined, forming a four-dimensional continuum known as space-time. This means that the two are not independent, they influence each other in profound ways. One of the most significant implications of relativity is the idea that time is not absolute. For instance, time can move at different rates depending on an object's speed and gravitational surroundings. An astronaut traveling close to the speed of light experiences time more slowly than someone on Earth. This phenomenon is known as time dilation. As a result, when the astronaut returns home, they will have aged less than their Earth-bound counterparts. This mind-bending twist to our perception of time reshapes our understanding of aging and the passage of time itself. In addition to time dilation, relativity also tells us that space can bend and warp due to the presence of mass. A massive object, like a planet or star, creates a distortion in the fabric of space-time. This bending of space is what we perceive as gravity, causing objects to attract each other. It challenges the Newtonian view that gravity is a force acting at a distance and shows that massive bodies warp the space around them, influencing how other objects move. Together, these concepts challenge our intuitions about the universe. They remind us that our perceptions of space and time are not as straightforward as they might seem. Instead, they are dynamic and ever-changing, influenced by speed, gravity, and the very structure of the cosmos. Through the lens of relativity, we come to appreciate the complex nature of the universe we inhabit, revealing a stunning interplay between time and space that deepens our understanding of reality itself. Wormholes capture the imagination of physicists and cosmologists alike, representing a fascinating concept in the realm of theoretical physics. These hypothetical passages, often described as shortcuts through space and time, challenge our understanding of the universe's structure. At their core, wormholes could provide a connection between distant regions in space or even between different times. This idea opens the door to exploring the very fabric of reality itself. The significance of wormholes lies not only in their potential implications for travel through the cosmos, but also in the insights they offer into the nature of gravity and space-time. According to the theories of general relativity proposed by Albert Einstein, massive objects cause a distortion in space-time that can create pathways through the universe. This leads us to ponder the possibilities of whether advanced civilizations could harness such structures for interstellar journeys, fundamentally altering our perception of distances in space. Furthermore, wormholes challenge our traditional views on causality and time travel. They provoke questions about the beginning and end of time, raising possibilities of interacting with the past or future. While this idea often treads the line between scientific theory and science fiction, it invites rigorous debate and research within the scientific community. The quest to understand wormholes may ultimately prove essential for a deeper comprehension of the universe's laws and how they govern everything from the smallest particles to the largest galaxies. Although no empirical evidence currently supports the existence of wormholes, their theoretical models encourage ongoing exploration in physics. They serve as a gateway into our understanding of exotic phenomena like dark energy and black holes. As researchers continue to delve into the complexities of wormholes, the journey itself might reveal more about the universe's mysteries than we can currently imagine. The concept of time travel has tantalized the imagination of humanity for centuries, presenting possibilities that stretch far beyond our current understanding of physics. While time travel into the future is theoretically possible, especially according to Einstein's theory of relativity, traveling back in time presents a more complex challenge that dives deep into the fabric of our universe. Einstein proposed that time is not a constant but can bend and stretch, influenced by gravity and speed. This means that if someone were to travel at nearly the speed of light, they could potentially experience time at a different rate than someone who remained stationary. For example, astronauts on a high-speed journey in space would age slightly less than those on Earth. This intriguing phenomenon, known as time dilation, has been celebrated and observed in experiments with particles and high-speed jets. However, the concept of reversing the flow of time, traveling back to previous moments in history, raises paradoxes and complications, like the famous grandfather paradox. This paradox questions what would happen if a time traveler prevented their own grandparents from meeting. The implications could unravel the very existence of the traveler themselves. Many authorities in theoretical physics introduce ideas such as wormholes, which could serve as shortcuts through space and time, although these remain purely speculative and have yet to be practically demonstrated. While traveling forward in time aligns with the principles of physics, and indeed has been observed, backward time travel remains within the realm of hypotheses and theoretical models. The mysteries of our universe may one day unveil more about the nature of time, but for now, these discussions inspire wonder and creativity, prompting us to ponder the fundamental nature of reality itself. The expansion of the universe profoundly influences our understanding of time, challenging perceptions that have long been taken for granted. Traditionally, time has been viewed as a constant, a reliable measure that ticks away evenly, regardless of the broader cosmic environment. However, as astronomers observe galaxies moving away from us, a phenomenon indicative of the universe's expansion, it becomes clear that time is interconnected with the fabric of the cosmos. As the universe expands, it stretches the very wavelengths of light, which in turn alters our perceptions of distant cosmic events. This can lead to a notion known as redshift, where light from stars and galaxies moving away from us appears to take on longer wavelengths, thus becoming redder. The observed change in light means that when we look at very distant objects in space, we are also looking back in time, seeing them as they were billions of years ago. This intertwining of light and distance fundamentally alters how we measure and interpret the passage of time across the universe. Furthermore, the expansion rate itself has implications for cosmic timelines. The rate at which the universe is expanding has accelerated, suggesting that distant galaxies will eventually move beyond our observable universe. This ongoing expansion raises intriguing questions about the future of cosmic time. As galaxies recede further, especially those beyond a certain distance, they will be drawn out of our sight, including any light they emit, effectively altering our cosmic horizon. Time, once thought to be unchanging, is now understood to be dynamic, influenced by the grand scale of the universe's expansion. The universe's growth not only shapes the structure of space itself, but also fundamentally redefines how we perceive time, merging our understanding of time with the nature of reality in a continuously evolving cosmos. This vision opens the door to contemplating profound questions about the origins, fate, and very fabric of existence as we navigate through the vastness of space and time. The concept of the multiverse suggests that our universe is just one of potentially countless others, each with its own unique set of physical laws and constants. This idea fundamentally challenges our understanding of reality, prompting us to reconsider our place in the cosmos. One of the significant implications of the multiverse theory is the nature of existence itself. If multiple universes exist, each with different variations of physical parameters, it gives credence to the idea that every possibility we can imagine might occur somewhere in the vast expanse of existence. Another fascinating implication is related to the nature of choice and free will. If there are infinitely many universes where every possible outcome of every decision exists, one might wonder whether our choices are as significant as we think. In some interpretations, every time we make a decision, the universe splits, and a new universe emerges with different outcomes based on those choices. This concept challenges traditional notions of narrative and consequence, inviting deeper contemplation about reality and the meaning of our experiences. The multiverse theory also helps address some of the most pressing questions in cosmology, particularly regarding fine-tuning. The universe appears to have constants and initial conditions that are incredibly specific. If they were even slightly different, life as we know it would not exist. The multiverse offers a potential explanation. In a vast sea of universes, it is not surprising that at least one would develop the necessary parameters for life. This could mean that rather than our universe being the only one with these fortunate conditions, it is simply one among many that happen to support life. Finally, the implications of the multiverse extend to our understanding of scientific inquiry itself. If multiple universes exist, the quest to study and observe them becomes daunting and philosophical. What methodologies can we use to explore something inherently unobservable? This thought experiment challenges our scientific frameworks and how we derive meaning from our universe, pushing the boundaries of how we define knowledge, existence, and reality. The multiverse concept invites us into an extraordinary dialogue about what it means to be a part of something infinitely larger than ourselves. The life of a star begins in vast clouds of gas and dust known as nebulae. These massive formations are the remnants of older stars that have exploded and spread their materials across the cosmos. Over time, gravity pulls the scattered particles in a nebula together, causing denser regions to form. As these clumps grow, they begin to collapse under their own gravity, drawing in more material and increasing in temperature and pressure. As the core of this collapsing region heats up, nuclear fusion begins. At this stage, the hydrogen atoms in the core start to collide and fuse, creating helium and releasing an incredible amount of energy in the form of light and heat. This marks the birth of a new star. Our Sun, along with countless other stars, formed in this manner from a nebula roughly 4.6 billion years ago. The surrounding material continues to fall into the star, allowing it to maintain its energy output. In the early stages, a star is surrounded by a rotating disk of gas and dust. This disk can give rise to planets, moons, and other celestial bodies, as material clumps together in a process akin to the one that formed the star itself. Thus, our solar system's planets, including Earth, formed from the very same nebula that birthed our Sun. Eventually, when a star like our Sun exhausts its hydrogen fuel, it will undergo a series of transformations, ultimately leading to its demise. However, the legacy of its birth in a nebula continues as it contributes to the cosmic cycle of stellar evolution, enriching the universe with the elements necessary for life. It is a beautiful reminder of how the universe recycles itself, creating new stars and worlds from the remnants of the old. The formation of planets within star systems is a fascinating process that begins in expansive clouds of gas and dust, known as molecular clouds. These clouds are primarily composed of hydrogen, helium, and other trace elements. Over time, the force of gravity causes areas within these clouds to collapse, creating dense regions. As these regions condense, they form a protostar at the center, surrounded by a rotating disk of material called a protoplanetary disk. Within this disk, tiny particles begin to collide and stick together, forming larger and larger bodies through a process known as accretion. Initially, these are small grains that gradually merge into larger clumps, which can reach sizes of asteroids or even small planets. As these protoplanets grow, their gravitational pull increases, allowing them to attract even more material from the surrounding disk. Some of these objects may become the building blocks of planets, while others can remain as smaller bodies, like asteroids and comets. As the young star ignites and begins nuclear fusion, it emits powerful solar winds that can blow away the remaining gas in the disk. This is a crucial moment, as it can halt the growth of planets that have not yet formed or completed their development. Generally, the dynamics of the disk can lead to varying outcomes, such as the formation of gas giants in the outer regions or rocky planets like Earth in the inner areas. It's all about distance from the star. Closer to the heat makes it hard for gases to condense, while further out, gas and ice can accumulate into massive planets. Moreover, interactions between these growing planetary bodies can lead to a diverse array of outcomes within a star system. Collisions can create moons, while gravitational forces can either help some planets keep their material or eject others into the far reaches of space. This dynamic interplay results in the myriad of unique planetary systems we observe across the universe today, each with their own set of moons, rings, and other celestial phenomena. Thus, the birth of planets is a complex dance of gravity, chemistry, and time, culminating in the incredible variety of worlds that now populate our galaxy. The evolution of planetary systems is a captivating journey that unfolds over billions of years, beginning with the cosmic leftovers of star formation. When a star ignites, the surrounding gas and dust begin to coalesce, gradually forming a rotating disk known as a protoplanetary disk. Within this disk, particles collide and stick together, giving rise to larger bodies called planetesimals. These planetesimals then gather into protoplanets, leading the way toward the diverse planetary systems we observe today. Several factors influence the development of these systems. One of the most significant is the mass and type of the star at the center of the system. A massive star tends to produce a more robust disk with higher temperatures, which affects the types of planets that can form and where they can form. For instance, rocky planets like Earth often emerge in the warmer inner regions, while gaseous giants like Jupiter typically develop farther out, where cooler conditions allow for the accumulation of vast amounts of gas and ice. Moreover, the dynamics of the protoplanetary disk play a crucial role. Turbulence within the disk can cause gas and dust to clump together in various ways, leading to the formation of planets of different sizes and compositions. Additionally, interactions between forming planets can significantly alter their orbits and influence their final arrangements. This gravitational dance often results in some planets being cast into distant orbits, while others may collide, leading to a rich variety of planetary configurations that we see across different systems. Over time, the planetary system continues to evolve. After the formation phase, processes such as planetary migration, where planets change their orbits due to interactions within the disk, and the potential of later collisions, can reshape the arrangement of planets. Furthermore, the presence of gas giants can impact terrestrial planets, affecting their potential for hosting life. Thus, each planetary system is a product of a complex interplay of factors, and studying their evolution gives us profound insights into our own solar system and beyond. Protoplanetary disks are a crucial aspect of the planet formation process, serving as the breeding grounds for new worlds. Formed from leftover material after a star ignites, these disks can span vast distances, often stretching out a few hundred astronomical units. Within them, particles collide and stick together, gradually forming larger and larger bodies. As the dust and gas swirl around the young star, they begin to clump together under the force of gravity. Over time, these clumps can grow through a process known as accretion, where they gather more material from the disk. Some of these growing bodies become planetesimals, which are building blocks of planets, while others may evolve into full-fledged planets or even larger structures, such as moons or dwarf planets. Protoplanetary disks also provide crucial insights into the chemical composition of emerging planetary systems. The materials found in these disks can reveal a wealth of information about the conditions in which planets form. For instance, the distribution of elements and compounds can indicate whether the planets formed close to the star, where heat might have vaporized volatile materials, or farther out, where ices and gases could survive. This understanding is essential for piecing together how different planets, including our own, came into existence. Moreover, protoplanetary disks are active environments characterized by turbulence and dynamic interactions. These processes not only facilitate planet formation, but also influence the orbits of nascent planets. Current astronomical observations continue to study these disks in varying stages to learn more about how planets, including potentially habitable ones, form and what conditions might foster life in various parts of the universe. The discovery of exoplanets, planets located outside our solar system, has revolutionized our understanding of the universe and our place within it. Before the first confirmed detection in the 1990s, our view of the cosmos was largely centered around our solar system and its planets. Now, we know that there are potentially billions of other worlds orbiting stars throughout the galaxy. Each new discovery broadens our horizons and invites us to rethink what is possible in planetary systems. Exoplanets come in a wide array of sizes and compositions, from gas giants larger than Jupiter to rocky planets that could be similar to Earth. This diversity challenges our previous assumptions about planetary formation and the conditions necessary for life. As astronomers continue to identify such a variety of exoplanets, we're beginning to understand that our solar system is just one of many, each with its own unique characteristics. This tantalizing perspective opens the door to the idea that other habitable environments may exist elsewhere in the universe, making the search for extraterrestrial life all the more compelling. Moreover, the methods used to discover these planets, such as the transit method and radial velocity technique, provide valuable insights into how we study celestial bodies. As our technology improves, we're able to detect smaller and more distant exoplanets, including those in the habitable zone of their stars, where conditions might be right for life. As a result, the universe seems more inviting and potentially teeming with life than we ever imagined, adding depth to our understanding of Earth's origins and its future. Ultimately, the discoveries of exoplanets have not only expanded the catalogue of known worlds, but have also ignited a sense of wonder about the potential for life beyond our planet. Each finding allows us to consider profound questions about existence, our place in the cosmos, and the possibilities of other intelligent beings pondering the same thoughts about their universe. This exploration continues to inspire curiosity and drive scientific inquiry into what lies beyond our blue planet. The quest to find signs of life beyond Earth is a thrilling endeavor that combines various fields of science, technology, and exploration. Scientists begin by identifying environments that could support life, drawing from our understanding of life on Earth. Extremophiles, organisms that thrive in harsh conditions on our planet, have expanded our ideas of where life could exist, suggesting that similar conditions elsewhere in the cosmos might also harbor life. Space missions play a crucial role in this search. Robotic spacecraft and landers, like the Mars rovers, are equipped with sophisticated tools to analyze soil and rock samples for organic compounds and microbial life. The Curiosity rover, for example, has searched for past habitable environments on Mars, revealing areas that once had liquid water, a key ingredient for life as we know it. Scientists also analyze the atmospheres of distant exoplanets for biosignatures, which are molecules that indicate biological processes. The presence of gases like methane or oxygen in particular ratios can suggest that life might exist there. Telescopes, both ground-based and in space, are essential in this hunt. They observe planetary atmospheres by looking for light signatures as stars shine through them. Instruments like the James Webb Space Telescope enhance our ability to detect these atmospheres, expanding our reach into the cosmos. By analyzing the light, scientists can infer the chemical composition and potential habitability of these far-off worlds. Furthermore, researchers are also turning to a new frontier, ocean worlds in our solar system like Europa and Enceladus. These moons are believed to have subsurface oceans beneath icy crusts. They are prime candidates for hosting extraterrestrial life. Upcoming missions aim to drill through the ice and sample the ocean directly, bringing us a step closer to answering the profound question of whether we are alone in the universe. With each discovery, scientists continue to refine their methods and expand their search, driven by the deep curiosity about our place in the cosmos. The quest for extraterrestrial life is one of the most tantalizing pursuits in modern science. Within our galaxy, the Milky Way, there are several key locations that scientists believe hold the greatest promise for harboring life. These include exoplanets, moons, and regions where conditions may mirror those found on Earth, promoting the potential for life. One significant focus is on exoplanets, which are planets orbiting stars outside our solar system. The habitable zone, often termed the Goldilocks zone, is where conditions are just right, neither too hot nor too cold, to allow liquid water to exist. So far, thousands of exoplanets have been discovered, with many located in this sweet spot around their stars. Observing the atmospheres of these planets for signs of water vapor, oxygen, and other life-supporting molecules is a critical component of our search. Another promising area lies among the icy moons of our solar system, particularly Europa and Enceladus. These moons orbit Jupiter and Saturn, respectively, and are believed to have subsurface oceans beneath their frozen crusts. The presence of liquid water, along with potential chemical nutrients from their ocean floors, creates an environment that could be conducive to life. Missions planned towards these moons aim to directly explore their icy surfaces and subsurface oceans for microbial life or even more advanced organisms. Additionally, astrobiologists are looking at regions like the galactic habitable zone in our galaxy. This is a specific area where conditions are thought to be more favorable for life to form, taking into account factors such as distance from the galactic center, chemical abundance, and stellar density. The exploration of these varied environments underscores humanity's enduring curiosity about life beyond Earth, driven by the hope that we are not alone in this vast universe. Extremophiles are astonishing organisms that thrive in conditions that would be lethal to most life forms on Earth. These remarkable creatures can be found in the deepest ocean trenches, in scorching hot springs, and even in highly acidic environments. Their ability to survive extreme temperatures, salinity, pressure, and radiation has not only expanded our understanding of life's resilience, but also expanded our imagination regarding where and how life could exist beyond our planet. By studying extremophiles, scientists are uncovering fundamental principles about life's adaptability. For instance, some extremophiles harness biochemical processes that allow them to convert toxic compounds into energy. This revelation prompts intriguing questions about the possibility of similar life forms existing in environments long thought inhospitable, like the icy moons of Jupiter and Saturn or the extreme conditions of Mars. If life can thrive in such harsh conditions on Earth, it is reasonable to speculate that it may do the same elsewhere in the cosmos. Additionally, extremophiles serve as a model for astrobiology, the field dedicated to the study of life beyond Earth. The discovery of extremophilic organisms shapes our criteria for identifying potential habitable environments in space. For example, scientists now consider subsurface oceans and other harsh environments on celestial bodies as viable candidates for hosting life, suggesting that these locations, once overlooked, might hold the key to finding extraterrestrial organisms. Lastly, understanding extremophiles can also inform future missions aimed at detecting alien life. Their diverse metabolic pathways could give us clues about potential biosignatures or the signs of life we might look for in other worlds. As we refine our search for extraterrestrial organisms, extremophiles remind us that life is incredibly versatile and that the universe may be filled with surprising forms of life just waiting to be discovered. The Drake equation, formulated in the early 1960s by astrophysicist Frank Drake, serves as a framework for estimating the number of active, communicative extraterrestrial civilizations in our Milky Way galaxy. By breaking down the question into several key factors, it attempts to provide a more scientific basis for discussions surrounding the search for extraterrestrial life. Essentially, the equation multiplies several variables, each representing a facet of what it takes for intelligent life to emerge and communicate across the vastness of space. The equation considers factors such as the average rate of star formation in our galaxy, the fraction of those stars that have planets, and the number of potentially habitable planets per solar system. Additionally, it takes into account the likelihood of life developing on those planets, the fraction of life that evolves into intelligent beings, and the lifespan of such civilizations capable of transmitting and receiving signals. By compiling data on these factors, scientists gain a clearer picture of the odds of encountering intelligent life. What makes the Drake equation intriguing is not just the numerical outcome, but its ability to spark discussions and investigations in astrobiology, astrochemistry, and planetary science. By examining each variable, scientists can explore the uncertainties associated with the emergence of life and intelligence. This ongoing research fuels our understanding of life's conditions and the universe's vast potential for diversity. The Drake equation serves as a starting point for scientific inquiry into one of humanity's most profound questions. Are we alone in the universe? Though its results depend heavily on the values assigned to each variable, the equation ignites our imagination about the cosmos and encourages further exploration. Each new discovery in astronomy and planetary science not only informs the equation, but also brings us one step closer to answering the age-old question of whether intelligent life exists beyond Earth. As we venture further into the cosmos, our quest to identify biosignatures, the chemical signs of life, has gained momentum thanks to revolutionary technologies. These advancements enhance our ability to explore exoplanets, moons, and other celestial realms, searching for the faint whispers of life beyond our Earth. One of the primary tools driving this discovery is spectroscopy, particularly when applied to light emanating from distant worlds. Spectroscopy allows scientists to break down light into its component colors, revealing the unique fingerprints of various molecules in an object's atmosphere. Recently developed instruments are being integrated into telescopes, both terrestrial and space-based. For instance, the James Webb Space Telescope is designed to analyze the atmospheres of exoplanets with unmatched precision. By capturing infrared light, this advanced observatory can detect complex hydrocarbons, water vapor, and even potential signs of biological activity. The sensitivity of these instruments allows them to pick up on the faintest signals far out in the cosmos where signs of life might exist. Moreover, technological strides in artificial intelligence and machine learning are transforming how we process and interpret data. These algorithms can sift through vast troves of astronomical data, identifying patterns and anomalies that may indicate the presence of biosignatures more efficiently than traditional methods. As these technologies evolve, they promise to accelerate our search, allowing us to analyze more data in shorter periods, thus bringing us closer to detecting potential life beyond Earth. Lastly, the development of small, specialized spacecraft capable of interplanetary exploration also plays a significant role. Missions targeting the icy moons of our solar system, like Europa and Enceladus, utilize advanced sensing technologies to probe beneath their frozen surfaces. By analyzing subsurface oceans and ejecta plumes, these missions aim to uncover organic compounds that could suggest the presence of life. Together, these technological advancements not only refine our methods of detection, but also deepen our understanding of where and how life might arise in the universe. The origin of life on Earth is one of science's most intriguing mysteries. Current scientific understanding suggests that life began in a primordial soup around 3 to 4 billion years ago. This theory posits that Earth's early environment, rich in basic building blocks like organic molecules, created the perfect conditions for life to emerge. These molecules likely formed through a combination of atmospheric conditions, volcanic activity, and energy from lightning or ultraviolet radiation. One of the leading hypotheses about how life began centers on the idea of abiogenesis. This process involves simple organic compounds gradually evolving into more complex structures. For instance, amino acids, the essential building blocks of proteins, may have assembled in the oceans, forming chains that eventually led to more complex molecules such as ribonucleic acid or RNA. RNA can store information and replicate itself, akin to modern-day genes, hinting at a transitional form of life that predates DNA. Research into hydrothermal vents offers another fascinating angle on life's origins. These underwater fissures release heated water rich in minerals. The unique environment around these vents could have sparked the first chemical reactions that led to biological systems, providing a stable setting where complex organic molecules could thrive. By studying microbial life that exists today in such extreme environments, scientists hope to uncover vital clues about how life might have first appeared. While many questions remain, researchers continue to develop experimental models in laboratories that simulate early Earth conditions, attempting to recreate the chemical pathways that could have led to life. Each new discovery adds a piece to the puzzle, enhancing our understanding of how life could have emerged in a vast, lifeless universe and ultimately transformed our planet into a thriving biosphere. The primordial soup theory offers a fascinating glimpse into the beginnings of life on Earth, proposing that the early oceans were rich in essential chemicals necessary for creating living organisms. This theory suggests that, under the right conditions, these primitive waters acted like a soup, allowing simple molecules to react and interact, gradually forming more complex organic compounds. This idea captures the imagination and helps illustrate how life might have emerged from non-living matter. One of the key features of the primordial soup theory is its emphasis on environmental conditions. It posits that factors such as lightning, volcanic activity, and ultraviolet radiation could have provided the energy needed for chemical reactions to take place. These elements created a kind of natural laboratory where the building blocks of life, like amino acids and nucleotides, could form from simpler substances. This process likely took millions of years, slowly morphing these small compounds into the complex structures we associate with living organisms. An iconic experiment conducted in the 1950s, known as the Miller-Urey experiment, bolstered this theory. Scientists Stanley Miller and Harold Urey simulated the conditions of early Earth by mixing water, methane, ammonia, and hydrogen in a sealed environment. By introducing electrical sparks to mimic lightning, they were able to produce amino acids, the fundamental components of proteins. This experiment demonstrated that organic molecules could indeed form in conditions thought to resemble those of primordial Earth, lending significant credence to the soup theory. In the grand narrative of life's origins, the primordial soup theory remains a cornerstone, inviting questions and ongoing research. While contemporary science has expanded our understanding of life's beginnings, including theories such as hydrothermal vents and extraterrestrial origins, the primordial soup continues to be a compelling entry point for exploring how life emerged from the inanimate. Each new discovery adds layers to this complex tale, encouraging us to ponder the remarkable journey from simple molecules to the diverse tapestry of life we observe today. Hydrothermal vents, found deep in the ocean, are sites of immense scientific interest, particularly concerning the origins of life on Earth. These vents release heated, mineral-rich water from beneath the Earth's crust, creating unique ecosystems that thrive in conditions previously thought to be inhospitable. The discovery of life forms living around these vents, despite the absence of sunlight, has propelled theories that life may have originated from similar extreme environments. The conditions at hydrothermal vents are strikingly different from those on the surface. They provide a cocktail of chemicals, such as hydrogen sulfide, which can be utilized by microbes as an energy source. This process, known as chemosynthesis, allows these organisms to thrive independently of sunlight, suggesting that life could exist in environments vastly different from our own. This challenges traditional ideas that life requires sunlight, fundamentally reshaping our understanding of how life could form elsewhere in the universe. One fascinating theory proposes that the first life forms emerged in alkaline hydrothermal vent systems. Here, the interaction between the hot vent fluids and the cold ocean water creates a suitable environment for chemical reactions. These reactions could have led to the formation of simple organic molecules, which are the building blocks of life. As these molecules accumulated, they may have eventually led to the development of more complex structures, paving the way for the evolution of living organisms. Furthermore, these vents could also provide clues about extraterrestrial life. The notion that life can arise in extreme conditions has implications for the search for life on other celestial bodies, such as Europe or Enceladus, moons that exhibit similar hydrothermal activity. By studying hydrothermal vents, scientists are not only unraveling Earth's past, but are also gaining valuable insight into the potential for life beyond our planet, igniting curiosity about the existence of life in the vast expanse of space. Meteorites serve as fascinating clues in the ongoing quest to understand the origins of life on Earth. These celestial visitors, remnants from the early solar system, carry within them the building blocks of life, including amino acids and organic compounds. Their journey through space and eventual landing on our planet sparks curiosity among scientists about how life may have begun, potentially suggesting that essential ingredients for life could exist beyond Earth. One of the most compelling aspects of meteorites is their role in the theory known as panspermia. This idea proposes that life, or at least its fundamental components, could be distributed throughout the universe via meteorites, comets, and other cosmic debris. If elements needed for life could survive the intense conditions of space travel, it raises the intriguing possibility that Earth was seeded with these crucial ingredients from elsewhere in the cosmos. In particular, certain types of meteorites, such as carbonaceous chondrites, have captured the interest of researchers. These meteorites contain a wealth of organic molecules that are critical in the formation of amino acids. Some studies have shown that these meteorites can produce amino acids even under conditions that mimic those of early Earth. This discovery tantalizes scientists with the notion that the building blocks of life may not just be indigenous to our planet, but may have originated in the vastness of space. In conclusion, meteorites are more than just space rock. They are potential time capsules of our cosmic history. By examining what these ancient travelers contain, scientists can piece together a narrative about how life may have started on Earth and perhaps even hint at life's existence elsewhere in the universe. The study of meteorites continues to enrich our understanding of life's origins, proving that the mysteries of our existence may lie in the stars above. Throughout Earth's history, major extinction events have acted as pivotal turning points, dramatically reshaping the course of evolution. Each event, whether it was caused by catastrophic volcanic eruptions, massive asteroid impacts, or significant climate shifts, has led to the loss of vast numbers of species. The most notable of these events include the Permian-Triassic extinction, often referred to as the Great Dying, and the Cretaceous-Paleogene extinction, which famously wiped out the dinosaurs alongside many other species. The aftermath of these extinctions created vast ecological openings, allowing for a reconfiguration of life on Earth. After the Permian-Triassic extinction, when nearly 90% of marine species and 75% of terrestrial species vanished, new evolutionary pathways emerged. This event set the stage for the rise of the dinosaurs and eventually the dominance of mammals, illustrating how extinction clears the stage for new forms of life that can adapt and thrive in the freed environments. Similarly, after the Cretaceous-Paleogene extinction, which took place about 66 million years ago, the mammalian lineage diversified dramatically. With dinosaurs gone, mammals, previously overshadowed and often small, underwent rapid evolution, leading to the emergence of many new species, including primates. The shift from dinosaurs to mammals is a prime example of how extinction can catalyze tremendous bursts of evolutionary creativity, driving the development of complex ecosystems filled with varied life forms. These transformative events in our planet's history underscore a fascinating principle in evolutionary biology. Sometimes, the removal of dominant species can unleash a potential that allows other organisms to fill ecological niches that were previously unavailable. It serves as a reminder of the resilience and adaptability of life on Earth, demonstrating that, in the face of overwhelming loss, new beginnings can arise, propelling the march of evolution forward. The theory of evolution provides a compelling framework for understanding the incredible diversity of life we see on Earth today. It posits that all living organisms share a common ancestor, and that over vast periods, species have changed and diversified through a process called natural selection. This process occurs when organisms with traits better suited to their environment are more likely to survive and reproduce. Over generations, these advantageous traits become more common within a population, leading to gradual adaptations and the emergence of new species. One key aspect of evolution is genetic variation, which arises from mutations, gene flow, and sexual reproduction. These changes in the genetic material create a range of traits within a population. When environmental pressures, such as climate changes, food availability, or predator-prey dynamics, come into play, the individuals best equipped to navigate these challenges thrive. This survival does not happen overnight, but rather unfolds over millions of years, giving rise to the vast array of species we observe in different ecosystems today. The fossil record is a crucial piece of evidence supporting the theory of evolution. Fossils reveal a historical progression of life forms and demonstrate how species have transformed over time. For example, by examining the skeletons of ancient creatures, scientists can trace morphological changes that indicate evolutionary relationships. The discovery of transitional fossils, such as the famous Archaeopteryx, illustrates how certain traits evolved, in this case, showing a link between reptiles and birds. In addition to the fossil evidence, genetic studies also illuminate the connections among species. By analyzing DNA sequences, researchers can determine how closely related different organisms are and trace their evolutionary paths. These modern techniques reinforce the idea of a shared ancestry and highlight how the process of evolution has shaped the biodiversity that blankets our planet, making it one of the most fascinating aspects of biological science. The mechanisms driving adaptation and change in living organisms are intricate and fascinating. At the core of this dynamic process is evolution, a fundamental scientific theory that describes how species adapt over time to their environments. The primary engine of evolution is natural selection, a principle first articulated by Charles Darwin. Simply put, organisms with traits that better suit their environments are more likely to survive, reproduce, and pass those advantageous traits on to their offspring. This gradual process leads to the emergence of new adaptations and sometimes entirely new species. In addition to natural selection, several other mechanisms contribute to adaptation. Genetic variation plays a crucial role as it provides the raw material for change. Organisms possess variations in their genetic makeup, and these differences can be expressed as diverse physical traits, behaviors, or physiological features. Mutations, which are random changes in DNA, also introduce new traits into a population. While not all mutations are beneficial, some may confer advantages that help organisms thrive in specific environments. Another important factor is gene flow, which occurs when individuals from one population breed with individuals from another. This exchange of genetic material can enhance genetic diversity and introduce new traits into a population, making it more adaptable over time. Conversely, genetic drift, especially in small populations, can lead to random changes in gene frequencies, potentially influencing how organisms adapt to their surroundings. Together, these mechanisms form a complex web of interactions that shape the evolution of life on Earth. Whether through the slow accumulation of small changes or through more significant shifts sparked by environmental changes, adaptation is an ongoing process that highlights the resilience and diversity of living organisms. The study of these mechanisms not only deepens our understanding of life, but also underscores the interconnectedness of all species on our planet. Mass extinctions are significant events in the history of life on Earth, characterized by the rapid loss of a large number of species. These events, which have occurred 5 times in the past, fundamentally reshape ecosystems and set the stage for new evolutionary paths. When dominant species disappear, ecological niches become available for other organisms, often leading to bursts of diversification. This phenomenon is sometimes referred to as adaptive radiation, wherein survivors rapidly evolve to fill the roles left vacant by extinct species. For instance, after the dramatic extinction of the dinosaurs around 66 million years ago, mammals, who previously occupied minor roles in the ecosystem, surged in diversity and size. They evolved into numerous forms, including the ancestors of humans. The extinction event provides a blank slate for evolutionary potential, allowing new adaptations to flourish, often leading to the emergence of entirely new species and groups. This illustrates how the removal of dominant life forms can enable lesser-known organisms to rise and adapt in ways that might not have been previously possible. Moreover, mass extinctions can also lead to the development of new evolutionary strategies. For example, the ability to adapt to changing environments can become a more critical survival skill post-extinction. This flexibility in evolutionary traits often results in a more complex and varied web of life as the surviving species develop new interactions with each other and their habitats. Ultimately, mass extinctions are pivotal moments that can redirect the course of evolution. They remind us that life is not a linear path. Rather, it is a dynamic process subject to influences from catastrophic events, environmental changes, and the relentless competition for survival. Each extinction opens the door for new life to emerge, illustrating the resilience of nature and the constant ebb and flow of evolutionary change. Humans are strikingly unique among the vast array of species on our planet, thanks to a combination of physiological, cognitive, and social adaptations. One of the most remarkable differences lies in our brain capacity and structure. The human brain is not only larger relative to body size compared to other animals, but it is also exquisitely organized for complex thinking and problem solving. This cognitive prowess allows us to develop language, create art, and engage in abstract reasoning, abilities that distinguish us from our closest animal relatives. Another adaptation that sets humans apart is our ability to walk upright. In other words, bipedalism. This mode of locomotion has freed our hands for tool use and manipulation, enabling us to create and utilize complex tools. As we evolved, the shift to standing on two legs offered benefit beyond just mobility. It also improved our field of vision, allowing us to survey our environment for potential dangers and resources. This combination of being on two legs and having dexterous hands contributed significantly to our survival and adaptability in a variety of habitats. Social cooperation is perhaps one of the most profound adaptations humans possess. Our species has developed intricate social structures and practices. This capacity for cooperation and communication enables us to work in teams, share resources, and provide care for one another, even beyond immediate family. These social bonds have allowed for the building of cultures, societies, and civilizations, which have advanced human knowledge and improved overall living conditions over millennia. Lastly, our adaptability to varied environments is a testament to human resilience. While many species are confined to specific habitats, humans have shown the remarkable ability to thrive in diverse climates, from the Arctic tundra to tropical forests. Our innovative use of technology, along with our ability to modify our surroundings, has enabled us to live in places once considered inhospitable. This unique combination of cognitive, physiological, social, and environmental adaptations underscores how we have distinguished ourselves on this planet, not just as survivors, but as a species that shapes the world around us. Genetic mutations play a crucial role in the process of evolution, serving as the raw material for genetic variation within populations. At their core, mutations are changes in the DNA sequence that can occur due to a variety of factors, including environmental influences, errors during DNA replication, or even random chance. These mutations can alter an organism's traits, potentially making it better suited to its environment. When a mutation confers an advantage that improves an organism's chances of survival and reproduction, it can be passed on to future generations, facilitating evolutionary change. Mutations can be classified into different types, such as point mutations, deletions, and insertions. Point mutations, for example, involve a change in a single nucleotide and can result in a minor change in protein function or even no effect at all. On the other hand, larger mutations, such as deletions or duplications, can have more significant impacts. While many mutations may be neutral or harmful, it is the beneficial ones that tend to persist through natural selection, becoming more common over time in a population. The concept of natural selection intertwines deeply with genetic mutations. As organisms with advantageous traits survive and reproduce, they pass these favorable mutations to their offspring. This process ultimately shapes the genetic landscape of the population. Over generations, such accumulated changes can lead to the emergence of new species and the adaptation of existing species to shifting environments. The interplay between genetic mutations and environmental pressures highlights the dynamic nature of evolution. Throughout Earth's history, numerous remarkable adaptations have arisen, like the long necks of giraffes, which are thought to have evolved due to competition for food in trees. This remarkable mechanism of mutation and selection is a foundational concept in our understanding of how life on Earth changes over time, providing a powerful lens through which we can examine the incredible diversity of life we see today. Biodiversity is the variety of life found in different ecosystems, encompassing everything from the smallest microbes to the largest mammals, and even the vast range of plants that populate our planet. This incredible tapestry of life plays a crucial role in the health and resilience of ecosystems, enabling them to withstand environmental stresses and adapt to change. At its core, biodiversity contributes to the stability and productivity of ecosystems, creating a symbiotic balance that benefits all living organisms. One of the key ways biodiversity enhances resilience is through redundancy. In any given ecosystem, multiple species can fulfill similar roles, meaning that if one species is threatened or declines, others can step in to maintain essential functions like pollination, nutrient cycling, and pest control. This overlap ensures that ecosystems are less vulnerable to disturbances, whether from climate change, disease, or human activity. For instance, if a specific pollinator species is reduced due to habitat loss, other pollinators can often assume that role, maintaining the reproductive processes of flowering plants. Furthermore, diverse ecosystems are generally more productive. Different species use resources like sunlight, water, and nutrients in various ways. This diversity promotes higher rates of photosynthesis and nutrient uptake, which can lead to greater overall biomass. Healthy ecosystems, supported by a rich array of life, provide essential services such as clean air and water, soil regeneration, and carbon sequestration, all of which are vital for human survival and for mitigating the effects of climate change. Lastly, biodiversity fosters natural systems that exhibit adaptive capacity. Species with diverse genetic backgrounds are often more capable of surviving changes in their environment, whether it's adapting to new diseases or shifting climates. Such genetic variety is like a safety net, ensuring that some members of a population can thrive even when conditions become tough. Protecting the rich tapestry of biodiversity is not just about preserving unique species. It is paramount for ensuring thriving ecosystems that can support life on Earth, including our own. Biodiversity is a crucial indicator of the health of our planet, yet today it faces an unprecedented array of threats. One of the primary factors is habitat loss. As human populations grow, natural habitats are transformed into urban areas, agricultural fields, and industrial sites. This loss of habitat not only endangers the species that depend on these environments, but also disrupts entire ecosystems, ultimately threatening the delicate balance that maintains life. Another significant factor is climate change. The rise in global temperatures alters weather patterns and shifts habitats, forcing species to adapt, migrate, or face extinction. Ocean acidification, driven by increased carbon dioxide absorption, impacts marine life, particularly coral reefs, which support a diverse range of organisms. As climatic conditions continue to change, many species struggle to survive, leading to a decline in biodiversity. Invasive species are also a formidable threat. These are organisms that are introduced to new environments, often unintentionally, and can outcompete native species for resources. They can disrupt food chains, introducing diseases and altering ecosystems in the process. This competition can lead to a decline or extinction of native species, further diminishing biodiversity and altering the landscape of the affected areas. Lastly, pollution, particularly from plastics and chemicals, poses severe risks to various species across the globe. Pollutants can contaminate water sources, soil, and air, affecting not only wildlife, but also human health. The cumulative effect of these factors is a concerning decline in global biodiversity, making it imperative for preservation efforts to be embraced urgently if we are to sustain the rich variety of life that signifies our planet. Studying extinct species provides a fascinating glimpse into the past that can significantly guide current conservation efforts. Every extinction holds a story about the factors that led to the loss of that species, such as habitat destruction, climate change, or interspecies competition. By understanding these historical contexts, scientists can identify the vulnerabilities of species that are currently endangered and develop more effective strategies for preserving them. One revealing aspect of extinct species is how ecosystems react to changes over time. For instance, examining the role of a long-gone predator can highlight the consequences of removing similar species today. This insight can guide conservationists in restoring balance to ecosystems, by ensuring that all necessary species are protected and, when feasible, reintroduced. It's a reminder of the intricate web of life where every organism has its part to play. Additionally, studying the genetic makeup of extinct species can illuminate traits that may benefit modern counterparts. This genetic insight enables scientists to enhance breeding programs for endangered species by identifying beneficial traits that emerged in the past. Such endeavors help ensure greater resilience against threats like diseases and climate fluctuations. Ultimately, the lessons learned from the extinction of species serve as both a cautionary tale and a valuable resource. By applying these insights, we can better understand our role in the ecosystem and strive to protect the biodiversity that is vital for the health of our planet. Understanding what has been lost can inspire proactive measures, reminding us that conservation is not just about saving what is endangered, but also about learning from the past to secure a thriving future. Genetic diversity is a crucial component of the survival and adaptability of various species. It refers to the range of genetic variations within a population. This diversity acts as a buffer against environmental changes, allowing populations to adapt and thrive under new conditions. When a population has low genetic diversity, it becomes more vulnerable to diseases, environmental shifts, and other stresses that could threaten its survival. Consider the example of a population of plants in a changing climate. If all individuals are genetically similar, they may all respond in the same way to changes in temperature or water availability. However, when there is a broad genetic base, some individuals may possess traits that enable them to withstand drought or resist diseases, while others might adapt better to different temperatures. This variety increases the chances that at least some individuals will survive and reproduce, thus ensuring the continuation of the species. In wildlife populations, genetic diversity plays a critical role in resilience. When animals face threats such as habitat loss, pollution, or climate change, those with different genetic traits may exploit alternative resources or develop new behaviors to ensure their survival. A genetically diverse population is akin to a well-stocked toolbox, providing a range of strategies for surviving in a changing world. Moreover, conserving genetic diversity is essential for maintaining the health of ecosystems. As different species interact within their environments, the survival of one species can often hinge on the genetic variety found in another. Ecosystems with rich genetic diversity tend to be more stable, productive, and better equipped to withstand environmental pressures. Therefore, protecting this diversity is not only vital for individual species, but also for the intricate web of life on Earth. Interdependent relationships within ecosystems create a delicate balance crucial for sustaining life. In every ecosystem, each organism plays a specific role, forming networks of connections that influence each other's survival and reproduction. These relationships can be symbiotic, such as mutualism, where both species benefit, or parasitism, where one benefits at the expense of another. This intricate web ensures that resources are utilized efficiently, promoting biodiversity and resilience within the system. For instance, consider the relationship between plants and pollinators. Flowers rely on insects and birds to spread their pollen, while these animals depend on nectar as a food source. This mutual dependency not only facilitates the reproduction of plants, but also supports the survival of various animal species. If one part of this relationship falters, it can have cascading effects throughout the ecosystem, threatening both the plants that require pollination and the animals that rely on those plants. Predator-prey dynamics further illustrate the importance of these interdependent relationships. Predators help control populations of prey species, preventing overgrazing or overpopulation, which can lead to resource depletion. This natural regulation keeps ecosystems healthy and supports a balanced food chain. Without predators, certain species could dominate, disrupting the balance and potentially resulting in the collapse of the ecosystem. Lastly, the interactions extend beyond the immediate relationships in food webs. Decomposers, like fungi and bacteria, break down dead organisms, returning vital nutrients to the soil. This recycling process is essential for the productivity of the ecosystem, enabling new plant growth to flourish. Ultimately, these interdependent relationships illustrate the interconnectedness of life, demonstrating how each organism contributes to the overall health and stability of its environment. Through understanding these connections, we gain insights into preserving the delicate balance of our ecosystems. Scientists define intelligence as the ability to learn, solve problems, adapt to new situations, and understand complex ideas. This definition is not limited to humans, it applies to a wide range of species. By examining various animals, researchers aim to uncover the unique ways intelligence manifests in different environments and circumstances. For instance, the intelligence of a dolphin may be evaluated through social behaviors and communication skills, while the problem-solving abilities of a crow might be assessed through its innovative tool use. Studying intelligence across species requires a multifaceted approach. Scientists often rely on behavioral tests that reveal cognitive capabilities such as memory, reasoning, and social interaction. One popular method involves the use of mazes or puzzles that challenge animals to think critically and navigate obstacles. This kind of testing allows scientists to measure not just the outcome, but also the processes involved in problem solving. Each species brings its own strengths and adaptations, making it essential for researchers to tailor their approaches to the specific traits and natural behaviors of the animals being studied. Additionally, researchers use observational studies to gain insights into social intelligence. Many animals, including primates and certain birds, demonstrate sophisticated social structures that require a nuanced understanding of relationships and hierarchy. By observing these interactions, scientists can gauge how intelligence influences social dynamics within groups. The observational data can reveal patterns of cooperation, communication, and even empathy, which all contribute to a deeper understanding of what intelligence means in these contexts. Ultimately, the quest to define and study intelligence across species challenges our preconceived notions of intelligence itself. As we continue to learn more about the cognitive abilities of different animals, we find that intelligence is a spectrum. Each species has evolved its unique skills and strategies that are perfectly suited to their environments. This ongoing exploration not only deepens our scientific knowledge, but also sparks awe at the diverse forms of intelligence present in the animal kingdom. In recent years, our understanding of animal cognition has expanded dramatically, revealing that many species possess remarkable intelligence and problem-solving abilities. Traditionally, humans have viewed intelligence as a unique human trait, but research has demonstrated that numerous animals exhibit complex behaviors and mental processes that challenge this notion. From clever crows to insightful dolphins, evidence suggests that cognitive capabilities are far more widespread in the animal kingdom than we once thought. One fascinating area of study involves the use of tools. Many animals, from chimpanzees to sea otters, have been observed using objects in their environment to aid in tasks such as fishing or cracking open shells. This tool use indicates not only an understanding of cause and effect, but also a level of foresight, as animals must anticipate the result of their actions. The New Caledonian crow, for example, has shown exceptional skill in crafting tools from twigs and leaves to extract insects from tree bark. Such abilities showcase a high degree of problem-solving and innovation. Communication is another key aspect of animal cognition that has gained attention. Researchers have uncovered complex communication systems in various species, particularly in social animals. Dolphins, for instance, utilize a series of clicks and whistles to convey information, navigate their environment, and even coordinate hunting strategies. These sophisticated interactions reveal that social dynamics and environmental challenges are significant drivers of cognitive development in non-human animals. Moreover, studies in behavioral ecology demonstrate that animals like elephants and dogs exhibit empathy, cooperation, and even deception. These traits highlight the richness of animal intelligence and offer clues about the evolutionary pathways that foster cognitive skills. As we continue to explore the depths of animal cognition, we find ourselves rethinking what it means to be intelligent, recognizing that the answers may be far more complex and nuanced than we once assumed. Consciousness, a profound and elusive aspect of human experience, has sparked curiosity among scientists, philosophers, and neurologists alike. From a scientific standpoint, consciousness is often viewed as a complex interplay of neural processes in the brain. At its core, consciousness involves our awareness of self, surroundings, and thoughts. Researchers have made significant strides in identifying specific regions of the brain associated with various conscious experiences, but a universal definition remains just out of reach. One impactful approach to studying consciousness is through the lens of cognitive neuroscience. This discipline examines how brain structures and functions correlate with conscious thought. Advanced imaging technologies such as functional magnetic resonance imaging (fMRI) allow scientists to observe brain activity in real time. For instance, experiments reveal that particular areas, like the prefrontal cortex, are activated during self-reflective tasks. This kind of research has helped to map the neural correlates of consciousness, shedding light on how information is processed and integrated in the brain. Additionally, theories like integrated information theory propose that consciousness arises from the way information is synthesized across various neural networks. It suggests that consciousness reflects the extent to which a system can integrate information, creating a unified experience. Meanwhile, global workspace theory posits that consciousness acts as a platform where information is made available to different cognitive processes, enabling us to act and respond to our environment. These theories offer distinct perspectives on how consciousness could manifest from biological processes. Despite these advances, the fundamental question of how subjective experiences emerge from neural activity remains one of the greatest mysteries in science. Many researchers emphasize that understanding consciousness is not only an inquiry into brain function, but also a philosophical quest that challenges our perceptions of reality and self-identity. As investigations continue, the quest to unravel consciousness promises to be as stimulating as it is complex, inviting us to ponder the essence of what it means to be aware. Neuroscientists are constantly delving into the intricacies of the human brain, a task that involves a multifaceted approach combining advanced technology and innovative methods. One of the key tools in their exploration is neuroimaging. Techniques such as magnetic resonance imaging, or MRI, allow researchers to visualize brain structures in remarkable detail. Functional MRI goes a step further by capturing blood flow changes in the brain, helping scientists identify which areas are active during different tasks. This non-invasive approach provides critical insights into how the brain processes information and responds to various stimuli. In addition to neuroimaging, neuroscientists employ electrophysiology to probe the brain's electrical activity. This technique involves using electrodes to measure electrical impulses generated by neurons. By monitoring these signals, researchers can better understand how neurons communicate and what happens during different mental states, such as learning, memory formation, or even when experiencing emotions. This direct observation of brain activity unveils the complex networks and pathways that underpin our thoughts and behaviors. Behavioral studies also play a vital role in understanding the brain. By observing how individuals react to different situations or stimuli, scientists collect data that links cognitive processes to specific neural mechanisms. Experiments can range from simple memory tests to complex decision-making scenarios, allowing scientists to paint a comprehensive picture of how brain functions translate into behavior. Such studies help identify the cognitive functions involved in tasks and reveal potential disruptions in neural activity related to conditions like anxiety or depression. Finally, advanced genetic and molecular techniques are being utilized to explore the brain's underlying biology. Studies of the genetic basis of brain function allow scientists to investigate how our DNA influences cognitive abilities and predispositions to neurological disorders. Additionally, the development of tools like optogenetics enables researchers to control specific neurons using light, revealing new insights into how different parts of the brain interact. Through these varied approaches, neuroscientists are unraveling the complexities of the human brain, making significant strides in understanding not only its structure and function, but also its remarkable capacity for adaptation and healing. Understanding consciousness remains one of the most profound challenges in the realms of science and philosophy. At its core, consciousness encompasses our awareness of ourselves and our surroundings. Despite significant advancements in neuroscience, psychology, and cognitive science, we still grapple with fundamental questions about what consciousness truly is and how it arises. Researchers often describe it as the mind's ability to experience thoughts, emotions, and sensory perceptions. Yet pinning down the essence of consciousness is incredibly elusive. One of the main obstacles lies in the subjective nature of conscious experience. Each individual's awareness is unique, shaped by personal thoughts, feelings, and perceptions. This subjectivity complicates scientific study because it is difficult to quantify or measure something that is inherently personal. Unlike physical phenomena that can be observed and tested objectively, consciousness often defies easy observation, leaving scientists to rely on indirect measures which may not capture its full complexity. Another challenge is the problem of the hard question of consciousness, a term coined by philosopher David Chalmers. This refers to understanding why and how physical processes in the brain result in subjective experiences. While we can map brain activity and relate it to behaviors or cognitive functions, the leap from neural activity to the rich tapestry of conscious experience remains mysterious. This leads to questions about whether consciousness is a byproduct of brain functions or if it exists in a fundamental way that we have yet to understand. As we delve deeper into the neural correlates of consciousness, we uncover fascinating insights, yet the answers also raise new questions. The exploration of altered states of consciousness, such as those induced by meditation, drugs, or trauma, reveals the flexibility and complexity of our conscious mind. Each of these avenues offers tantalizing glimpses into the workings of consciousness, but also highlights how much we have yet to learn. Ultimately, the pursuit of understanding consciousness interweaves with inquiries into the nature of reality itself, inviting each of us to ponder our own experience of being alive. In recent years, advancements in telescope technology have revolutionized our understanding of the universe. One of the most significant developments is the deployment of the James Webb Space Telescope, which began its scientific observations in July 2022. With its ability to observe infrared light, Webb can peer deeper into space than ever before, allowing astronomers to uncover the formation of stars and galaxies from the dawn of time. This capability offers insights into the early universe, potentially illuminating how galaxies formed and evolved. Another exciting advancement is the emergence of ground-based telescopes equipped with adaptive optics. These systems correct for atmospheric distortions, granting astronomers a clearer view of celestial objects. For example, the extremely large telescope, currently under construction, aims to be the largest optical telescope in the world, boasting an aperture of 39 meters. With such immense capability, this telescope can observe exoplanets, identify their atmospheres, and delve into the mysteries of dark matter and dark energy. Moreover, radio telescope technology has also witnessed a remarkable transformation. Projects like the Square Kilometre Array are set to drastically enhance our ability to detect faint radio signals from distant cosmic phenomena. This unprecedented sensitivity will enable the study of the early universe and the mapping of cosmic structures in greater detail than ever before, revealing the intricate tapestry of galaxies and other celestial bodies that populate our cosmos. As we continue to innovate in telescope technology, the universe unveils its secrets at an astonishing pace. Each new discovery not only deepens our understanding of the cosmos, but also inspires a sense of wonder and curiosity about our place in the vast expanse of space and time. These scientific advancements remind us that we are on the very brink of a new understanding of the universe, and the possibilities for discovery are truly limitless. Space missions have profoundly transformed our understanding of the solar system, uncovering secrets that were once hidden beyond the reach of earthly observations. Before these missions began, our knowledge was primarily based on telescope observations and mathematical predictions. However, sending spacecraft directly to other planets, moons, and celestial bodies has provided a treasure trove of data, leading to unprecedented discoveries. Take, for instance, the Voyager missions, which launched in the late 70s. Voyager 1 and Voyager 2 were designed primarily for flybys of Jupiter and Saturn, but they ended up revealing far more than astronomers had anticipated. These spacecraft took breathtaking images of the planets and their moons, revealing active volcanoes on Io, the intricate ring system of Saturn, and the harsh yet fascinating surface of Titan, Saturn's largest moon. The data sent back by Voyager has been invaluable in reshaping our understanding of planetary atmospheres, tectonics, and even the potential for life beyond Earth. Closer to home, missions like the Mars rovers have fundamentally changed our perception of the Red Planet. Rovers like Curiosity and Perseverance have explored the Martian terrain, conducting experiments and searching for signs of past life. Their findings suggest that Mars once had liquid water and a suitable climate for life, sparking renewed interest in colonization and the search for extraterrestrial organisms. Each discovery from Mars not only alters our understanding of the planet itself, but also encourages humanity to reconsider what constitutes habitable environments. Moreover, missions to the outer planets, such as Juno's study of Jupiter and Cassini's exploration of Saturn, have provided insights into the formation and evolution of our solar system. These missions have revealed the complex dynamics of planetary atmospheres, magnetic fields, and even the geology of icy moons, like Europa and Enceladus, which harbor subsurface oceans. As we continue to send missions further into space, each new piece of knowledge builds on the last, enriching our understanding and fueling our curiosity about what lies beyond our celestial neighborhood. International collaborations are vital to the success of space exploration, shaping a collective approach to some of humanity's most ambitious scientific goals. These partnerships pool resources, expertise, and technology from various countries, enabling not just greater efficiency, but also a broader perspective on the challenges we face beyond our planet. By combining efforts, nations can tackle complex missions that would be far more daunting if attempted in isolation. One of the most striking examples of such collaboration can be seen in the International Space Station, which brings together space agencies from the United States, Russia, Europe, Japan, and Canada. This orbiting laboratory serves not just as a hub for research, but also as a testament to what can be achieved when countries work together. The research conducted there strengthens our understanding of life in space, human health, and advanced technology, revealing the interconnectedness of different fields of science. Moreover, international partnerships often drive advances in technology that benefit more than just the space industry. For instance, innovations developed for space missions have contributed to medical imaging, disaster response, and telecommunications here on Earth. By sharing knowledge and experience, countries enhance their technical capabilities, fostering an environment of innovation that extends well beyond the confines of space exploration. Perhaps most importantly, international collaborations foster a sense of global unity in confronting common challenges. Exploring the cosmos brings humanity together, highlighting our shared responsibility to protect our planet while reaching for the stars. These partnerships inspire future generations to think beyond borders and instill a lasting belief in the power of cooperation in pursuit of knowledge and discovery. Artificial intelligence has revolutionized our understanding of the universe, enabling scientists to process vast amounts of data quickly and efficiently. Traditionally, analyzing astronomical data required substantial human effort and time. However, AI algorithms can sift through millions of images and datasets in mere moments, identifying patterns and anomalies that might elude even experienced researchers. This capability enhances our ability to track celestial objects from distant galaxies to nearby asteroids. One key area where AI has made a significant difference is in the detection of exoplanets. By analyzing light curves from thousands of stars, AI systems can spot the subtle dimming that occurs when a planet passes in front of its star. This method, called the transit photometry technique, has led to the discovery of thousands of potential new worlds. AI not only speeds up this discovery process, but also improves accuracy, pinpointing which planets might be most likely to host life. Moreover, machine learning algorithms assist in classifying galaxies, identifying their shapes, sizes, and types with remarkable precision. This has profound implications for understanding cosmic evolution and the formation of large-scale structures in the universe. By organizing galaxies into meaningful categories, AI helps astronomers draw connections and develop theories about how the universe has evolved over billions of years. Lastly, artificial intelligence is set to play a critical role in the future of space exploration. As missions to Mars and beyond become more ambitious, autonomous systems driven by AI are needed to make real-time decisions and navigate uncharted terrains. By harnessing the power of AI, we are forging a new path in our quest to unravel the mysteries of the cosmos, ensuring that every discovery brings us closer to understanding our place in it. As we look to the future, space agencies like NASA and the European Space Agency, or ESA, have set their sights on ambitious goals that promise to expand our understanding of the universe and enhance our capabilities in space exploration. One of the most significant objectives on the horizon is the return of humans to the Moon, specifically through NASA's Artemis program. This initiative aims to land the next astronauts on the Moon by the mid-2020s, including the first woman and the next man on the lunar surface. NASA envisions the lunar exploration not just as a destination, but as a stepping stone for future missions to Mars. In parallel, ESA is concentrating on its own lunar ambitions. They are collaborating with NASA on the Artemis program and have plans to contribute essential technologies, such as the European Service Module for the Orion spacecraft. ESA is also advocating for sustainable lunar exploration through its Moonlight initiative, which aims to create a lunar communication and navigation network that will support both governmental and commercial missions to the Moon. Meanwhile, Mars continues to be a focal point for exploration. NASA's Perseverance rover is already on the Red Planet, tasked with searching for signs of ancient life and collecting samples for future return missions. ESA, in collaboration with other space agencies, is also working on the Mars Sample Return mission, which aims to bring Martian soil and rock samples back to Earth for detailed analysis. The exploration of Mars is not merely about finding life. It holds the potential to unlock secrets about the solar system's history and the processes that led to the development of planets. Lastly, both agencies are looking to expand their reach further into the cosmos with telescopes and probes designed to explore exoplanets and distant celestial bodies. NASA's James Webb Space Telescope is already revolutionizing our understanding of the early universe, while ESA's mission to the outer solar system, such as the Jupiter Icy Moons Explorer, aims to explore the habitability of celestial bodies like Europa and Ganymede. These initiatives reflect humanity's insatiable curiosity and the quest to uncover the mysteries of the universe, signaling an exciting era of exploration and discovery. Astrobiology serves as a fascinating intersection between astrophysics and biology, aiming to unravel the profound mysteries surrounding life beyond our planet. This dynamic field explores the origins, evolution, and potential for life across the cosmos, not just focusing on Earth, but also extending to other celestial bodies. By studying extreme environments on Earth, such as volcanic regions or deep-sea vents, scientists gain insights into the resilience of life and how it might survive in similar conditions elsewhere in the universe. At its core, astrobiology seeks to answer the fundamental questions. How does life begin? What constitutes a habitable environment? It examines the chemical building blocks of life and how they might form under different cosmic conditions. Engaging in this multidisciplinary approach allows astrobiologists to predict where life could potentially thrive, whether on Mars, the icy moons of Jupiter, or exoplanets located in the habitable zones of distant stars. Astrobiology heavily relies on data from space missions, telescopes, and laboratory experiments. For instance, the discovery of water ice on Mars and the detection of organic molecules on comets indicate that the ingredients for life might be more common throughout the universe than previously thought. Such findings drive home the idea that while Earth is unique, it may not be alone in its ability to support life. Moreover, astrobiology delves into the future of life, contemplating how organisms might adapt to different celestial environments and the implications of discovering extraterrestrial life on our understanding of biology. This awe-inspiring exploration not only deepens our comprehension of life's possibilities across the universe, but also our own existence within it, painting a larger picture of what life truly means in a vast and mysterious cosmos. Scientists employ a variety of sophisticated tools and techniques to simulate extraterrestrial environments, aiming to understand the conditions found beyond Earth. One of the most common methods involves the use of specialized facilities known as planetary simulation chambers. These chambers can recreate the extreme temperatures, pressures, and atmospheric compositions of other worlds, such as Mars or the icy moons of Jupiter and Saturn. By manipulating variables like gravity and radiation levels, researchers can mimic the surroundings that potential extraterrestrial life forms might encounter. In addition to simulation chambers, scientists utilize computer modeling and simulations. Advanced software allows researchers to create complex models of planetary atmospheres and surface interactions. These simulations take into account factors such as solar radiation, geological processes, and even potential biological activities. By inputting different variables, scientists can explore a wide range of scenarios and predict how various environments might change over time. Field studies also play a critical role in understanding extraterrestrial conditions. Earth-based analog sites, such as the dry valleys of Antarctica or the extremes of volcanoes and deserts, provide invaluable insights into how life might adapt in harsh environments. Here, scientists can study extremophiles, organisms that thrive in inhospitable conditions, offering clues about the potential for life elsewhere in the cosmos. Moreover, integrated robotic systems contribute to these efforts by conducting experiments in simulated environments. These robots can carry out tasks ranging from soil analysis to atmospheric sampling. Together, these tools not only enhance our understanding of other worlds, but also help prepare for future exploration missions as we seek to uncover the mysteries that lie beyond our home planet. Astrobiologists study life in extreme conditions on Earth to gain insights into what life might be like on other planets, especially those that exist far from our Sun. These scientists seek environments that mimic the harsh conditions found in places like Mars, Europa, or even the atmospheres of distant exoplanets. Ice-covered lakes, boiling hot springs, deep ocean vents, and high-altitude locations provide rich fields for research. By observing and analyzing the unique life forms in these extreme settings, astrobiologists create models that help them speculate about the potential for life elsewhere in the universe. One fascinating example is the discovery of extremophiles, organisms that thrive in environments once deemed uninhabitable. For instance, some microbes can survive at extremely high temperatures, while others can endure intense radiation. These findings are groundbreaking as they broaden our understanding of the limits of life. If life can persist in such extreme conditions on Earth, it raises intriguing questions about its existence on other celestial bodies where conditions are similarly harsh. Astrobiologists often employ a multidisciplinary approach, utilizing techniques from microbiology, geology, and environmental science. They conduct field studies in remote locations, collecting samples and data that reveal how life adapts to its environment. Laboratory experiments further mimic these extreme conditions, allowing researchers to observe responses in real time. This experimental data becomes critical when evaluating planetary conditions that might support or inhibit life. Ultimately, the study of life in extreme Earth environments not only enhances our understanding of biodiversity on our planet, but also shapes the astrobiological questions we ask about the cosmos. Each discovery about life's adaptability here informs our search for signatures of life beyond Earth. By uncovering the resilience of life in extreme conditions, astrobiologists offer us a window into the possibilities that may lie across the universe. The discovery of water ice on other celestial bodies holds immense significance for both our understanding of the universe and the potential for future exploration. Water is essential for life as we know it, and finding it beyond Earth opens up exciting possibilities. Whether on the Moon, Mars, or moons of the outer planets like Europa and Enceladus, the existence of water ice suggests that these locations could harbor environments where life might exist or may have existed in the past. One of the most promising aspects of finding water ice is its potential use for human exploration. For instance, if we establish a human presence on Mars, accessing local water ice could provide astronauts with drinking water, breathable oxygen, and even fuel. In situ resource utilization, or using materials found on other celestial bodies, makes long-term missions more feasible, reducing the need to transport everything from Earth. Additionally, the presence of ice on celestial bodies can give scientists clues about the history and evolution of our solar system. For example, the distribution and composition of water ice can indicate the past climatic conditions and geological processes on these bodies. This information helps researchers piece together the puzzle of how different environments have shaped planetary development. Moreover, the search for extraterrestrial water adds another layer to our quest to find life beyond Earth. By studying where water ice exists and how it interacts with its surroundings, scientists can form better hypotheses on how life might thrive in these alien conditions. These discoveries propel our quest for knowledge, encouraging further exploration missions and igniting our curiosity about the possibility of life in our vast universe. The discovery of complex organic molecules in space has profound implications for astrobiology, the scientific field that explores the potential for life beyond Earth. These molecules, which include amino acids and hydrocarbons, serve as the building blocks of life. Their presence in interstellar clouds, comets, and even the atmospheres of other planets suggests that the fundamental components necessary for life are far more widespread than previously thought. One of the most striking discoveries came from meteorites containing organic compounds that had formed in space before landing on Earth. These findings raise intriguing questions about the origins of life on our own planet. If life's precursors were delivered from space, perhaps Earth is not the only place in the universe where life might arise. This has fueled interest in exploring other celestial bodies, such as Mars and the moons of Jupiter and Saturn, where similar organic molecules might exist. Additionally, the study of these molecules has advanced our understanding of the processes that lead to life's formation. Observations from telescopes have revealed a pipeline of complex chemistry occurring in space, where simple organic compounds undergo transformations in environments subjected to radiation and extreme temperatures. This research suggests that the universe functions as a vast laboratory for chemistry, potentially giving rise to the necessary conditions for life to emerge. As we continue to uncover organic chemistry in the cosmos, astrobiology not only reassesses the conditions needed for life, but also enriches our understanding of how common or rare life might be across the universe. The search for extraterrestrial life is now framed within a context where the ingredients for life are not unique to Earth, but rather scattered throughout the galaxy, waiting to be discovered. The idea of colonizing other planets has captivated humanity for generations. With advancements in technology and a growing understanding of the challenges posed by cosmic environments, the feasibility of establishing human settlements beyond Earth is slowly coming into focus. However, while exciting, the journey towards interplanetary colonization is fraught with significant hurdles. Mars is often identified as the most viable candidate for colonization. Its proximity to Earth and some Earth-like qualities, such as a day length similar to ours, make it an intriguing option. However, Mars presents extreme conditions, including harsh temperatures, a thin atmosphere, and high radiation levels. Any attempts to colonize this red planet will require innovative solutions, such as creating sustainable habitats that can protect humans from radiation and cultivating food in a barren landscape. Beyond Mars, moons like Europa and Titan also capture interest due to their potential subsurface oceans and atmospheres that might support life. Yet, these locations bring their own set of obstacles. Europa's icy shell hides a liquid ocean beneath, but reaching it and existing there would demand technologies that are still in the theoretical stage. Titan, Saturn's largest moon, has a thick atmosphere and lakes of methane, but its extreme cold and unique chemistry raise questions about human survival. While the goal of colonizing other planets is exciting, it remains largely aspirational in the near future. As space agencies like NASA and private enterprises like SpaceX press onward in their explorations, we will continue to learn about the challenges and possibilities that lie beyond our home planet. The dream of living on another world may inch closer to reality, driven by human ingenuity, but the timeline remains uncertain, dependent not only on technological advancements but also on international collaboration and ethical considerations. As humanity looks to establish a presence on other celestial bodies, a myriad of ethical considerations arise. Central to the debate is the question of planetary protection, which seeks to avoid contamination of both Earth and extraterrestrial environments. When we send missions to other planets or moons, we risk not only the introduction of Earth-based organisms to pristine ecosystems, but also the potential loss of unique extraterrestrial life forms that we have yet to discover. This creates a moral imperative to tread carefully on new worlds. Another significant consideration is the potential exploitation of extraterrestrial resources. The idea of mining asteroids or extracting materials from other planets raises questions about ownership and stewardship. Who has the right to claim resources in space? Is it a free-for-all, or should there be regulations in place to ensure that any extraction is done sustainably and equitably? These dilemmas mirror many terrestrial resource conflicts, prompting us to think about how to prevent repeating those mistakes far from home. Moreover, establishing human settlements on other celestial bodies raises issues of colonialism and the rights of potential native life forms. Even if we find no life, the ethical implications of altering landscapes and ecosystems cannot be ignored. We must consider whether we have the right to modify or inhabit these worlds at all. This pushes us to define what it means to be a responsible, ethical explorer of the universe, particularly as we confront our history of exploitation on Earth. Finally, there are profound questions concerning the implications of a human presence in space for our societal values. As we embark on this journey, we face choices about how to govern our activities beyond Earth. These decisions could shape not just our exploratory missions, but also the foundation of a future spacefaring civilization. Balancing ambition with responsibility will be crucial as we step into this new frontier. Long-duration spaceflights bring about a fascinating array of effects on both the human body and mind. As astronauts venture beyond Earth's protective atmosphere, they encounter a microgravity environment that dramatically alters the way their bodies function. One of the most notable physical changes is muscle atrophy. Without the constant pull of gravity, muscles can weaken and diminish in size due to disuse. This occurrence leads astronauts to engage in rigorous exercise routines on board to maintain their strength and prevent these detrimental effects. Bone density is another critical area impacted by extended time in space. Research indicates that astronauts can lose as much as 1 to 2% of their bone mass each month while in microgravity. This loss makes bones more porous and susceptible to fractures. To combat these changes, dietary adjustments and specialized medical countermeasures are essential. Calcium and vitamin D intake, combined with targeted exercise regimens, help to mitigate these risks. But the problem persists and demands continuous research. The mind, too, faces challenges during long missions. Astronauts are isolated in confined spaces, making psychological health a paramount concern. Prolonged separation from family and friends, combined with the stresses of living in a limited environment with limited resources, can lead to feelings of loneliness and anxiety. Counteracting these feelings involves maintaining communication with loved ones, engaging in recreational activities, and fostering teamwork among crew members to build camaraderie. Interestingly, a phenomenon known as the overview effect can alter astronauts' perspectives on life when they view Earth from space. This shift in awareness often leads to a deeper appreciation for our planet and a heightened sense of responsibility towards its care. As science continues to unravel the complexities of how space travel affects human physiology and psychology, the insights gained could have profound implications not only for astronauts, but also for our understanding of human resilience in extreme conditions. Sustaining human life on Mars or other planets requires groundbreaking technologies that can replicate essential conditions from Earth. Firstly, life support systems are crucial. These advanced systems must provide breathable air, drinking water, and food. In particular, technologies for water extraction from Martian soil and atmospheric humidity offer promising avenues for maintaining human hydration. Efficient recycling systems that purify waste and generate clean air will also be vital, minimizing the need for resupplies from Earth. Another significant technology involves energy production and storage. Solar power is likely the primary energy source due to the abundance of sunlight on Mars, although its effectiveness diminishes during dust storms. Innovative solar panels or possibly even nuclear power systems, which offer consistent energy supply, are being explored. Energy is not just needed for machinery. It will also be essential for hydroponic or aeroponic farming, enabling astronauts to grow fresh food on-site, thus reducing dependence on pre-packaged food supplies. Radiation protection technologies form another critical barrier to long-term habitation. Mars lacks a thick atmosphere and strong magnetic field, exposing its surface to harmful cosmic radiation. Engineers are developing habitats that incorporate shielding from radiation using Martian regolith, the powdery soil that covers the planet. This not only utilizes local materials, but also ensures a safer living environment for astronauts. Lastly, effective communication and transportation technologies are indispensable for human life on other planets. Reliable systems will need to exist for sending and receiving information between Mars and Earth and for navigating the Martian terrain. Rovers, drones, and even advanced vehicles for long-distance travel across the harsh landscape will be essential for exploration and resource gathering, laying down the infrastructure for future Martian colonization. Together, these technologies form a complex web of systems that will support life far beyond our planet. Public interest in space exploration plays a significant role in shaping scientific and governmental agendas. When the public shows enthusiasm for space missions, it often leads to increased funding and support for agencies like NASA and its global counterparts. This interest can manifest through popular media, educational programs, and community events that make space exploration accessible to everyone. As people engage with these topics, they begin to advocate for more ambitious projects, often pushing for manned missions to Mars or the establishment of bases on the Moon. Governments, aware of the public's fascination with space, recognize the political and economic potential of promoting space initiatives. A well-supported space program not only fosters national pride, but also positions the country as a leader in technological advancement. As a result, politicians often leverage this public interest when drafting budgets or proposing new missions. When citizens rally behind space exploration, it can lead to bipartisan support for funding and resources, allowing scientists and engineers to carry out innovative projects. Moreover, public engagement in space exploration fosters educational initiatives that inspire the next generation of scientists and engineers. Schools incorporate space-themed curriculums which stimulate students' curiosity about the universe. In turn, this increase in interest can lead to a well-prepared workforce ready to tackle the challenges of space exploration and technology. The cultural significance of space exploration often permeates various sectors, encouraging cross-disciplinary collaboration that benefits multiple areas of science. Ultimately, the interplay between public enthusiasm and governmental objectives creates a dynamic feedback loop. As public interest fuels scientific inquiry and funding, successful missions in turn stimulate further fascination, promoting a continuous cycle of exploration and discovery. This relationship underscores the importance of keeping the public engaged and informed about the wonders of the cosmos, ensuring that the quest to understand our universe remains a shared endeavor. Quantum mechanics stands as a pillar of modern physics, but it's also laden with perplexities that continue to intrigue scientists. One of the most foundational principles is the concept of superposition. In simple terms, this means that particles can exist in multiple states or locations at once until they are observed or measured. This challenges our everyday understanding of reality, as we don't experience objects being in two places simultaneously. Instead, we see them in distinct states. The famous thought experiment involving Schrödinger's cat highlights this baffling peculiarity, where a cat can be considered both alive and dead until it is observed. Another intriguing principle is entanglement. When two particles become entangled, the state of one particle instantaneously influences the state of the other, regardless of the distance separating them. This phenomenon seems to defy the classical idea of locality, where information cannot travel faster than the speed of light. Einstein famously referred to this as spooky action at a distance, reflecting the confusion many scientists feel about how entangled particles can remain connected across vast distances. The uncertainty principle, introduced by Werner Heisenberg, adds yet another layer of complexity. It articulates that certain pairs of physical properties, like position and momentum, cannot both be precisely measured at the same time. The more accurately one is known, the less accurately the other can be determined. This uncertainty is not due to limitations in measurement technology, but is an inherent property of quantum systems. For many, this principle disrupts the very notion of determinism that dominated classical physics. Lastly, the wave-particle duality challenges our perception of what a particle is. Particles such as electrons and photons exhibit both wave-like and particle-like behaviors, depending on how they are observed. This duality leads to the realization that the nature of matter and energy is more complex than previously understood, blurring the lines that categorize them. Together, these principles not only baffle scientists, but also fuel ongoing research and philosophical debates, showcasing the intricate and enigmatic nature of the universe at a quantum level. Quantum entanglement is one of the most fascinating and perplexing phenomena in the realm of quantum mechanics. At its core, entanglement describes a unique relationship between two particles that become intertwined in such a way that the state of one instantly influences the state of the other, regardless of the distance separating them. This unexpected connectivity defies our classical understanding of reality, which relies on the idea that objects only affect each other through direct interaction in a local environment. In the classical world, if you want to influence an object, you need a direct line of communication or an interaction that happens over a measurable distance. However, quantum entanglement suggests that when particles are entangled, their states are linked in a fundamental manner. When scientists measure the state of one entangled particle, the state of the other particle, no matter how far away, appears to change immediately. This notion challenges the classical principle of locality, which posits that information cannot travel faster than the speed of light. Entanglement raises profound questions about the nature of space, time, and information itself. Furthermore, Quantum entanglement implies a level of interconnectedness that is not easily visualized. It suggests that at a fundamental level, the universe operates in a way that transcends the separateness we observe in our everyday experiences. This interconnectedness can invoke a sense of wonder as it prompts us to reconsider our perceptions of reality. Is the universe a collection of isolated objects, or is it a cohesive, interconnected fabric that defies our intuitive notions? The implications of quantum entanglement extend far beyond theoretical physics. They are the basis for emerging technologies such as quantum computing and quantum cryptography, which promise to revolutionize how we process information and secure communications. As we increasingly explore the quantum realm, we find ourselves grappling with the paradoxes it presents, urging us to rethink our understanding of reality itself and our place within the cosmos. The observer effect in quantum physics highlights a profound insight into the nature of reality at the microscopic level. Essentially, it suggests that the act of observation can influence the system being observed. This phenomenon primarily relates to particles, where attempting to measure or observe their state can alter their behavior. It's not merely about the act of looking, it's about how the observation interacts with the quantum system. In practice, this means that when scientists measure a particle's properties, such as its position or momentum, they inevitably affect those properties. For instance, if researchers attempt to determine the exact location of an electron, the measurement itself may cause the electron to shift from its original position. This contributes to a rich tapestry of experimental results that challenge our traditional understanding of reality as being fixed and predetermined. Instead, it portrays a world where potentiality and observation are intricately entwined. Furthermore, the observer effect raises important questions about the role of consciousness and measurement in determining the state of a quantum system. Are we, as observers, influencing the outcome of these particles? Or is there an underlying reality that exists independently of our measurements? This uncertainty doesn't just sit within the realms of theoretical discussions, it has practical implications for technologies like quantum computing and quantum cryptography, which aim to utilize these quantum phenomena. The observer effect is significant because it suggests that the universe at its most fundamental level does not behave like our everyday experiences suggest. It inspires curiosity and exploration, urging scientists and enthusiasts alike to delve deeper into the mysteries of quantum mechanics and its implications for understanding the universe we inhabit. Quantum theories and cosmology are two pillars of modern physics, each providing unique insights into the workings of the universe. At first glance, these fields seem worlds apart, with quantum theories describing the behavior of particles on the tiniest scales, while cosmology examines the vast expanses of the universe itself. However, their intersection is where some of the most profound questions about reality arise. One of the key areas where these fields meet is in the study of the early universe, particularly during the moments after the Big Bang. Quantum fluctuations are believed to have been fundamental in shaping the distribution of matter and energy, leading to the large-scale structures we observe today, like galaxies and galaxy clusters. These fluctuations arise from the uncertainty principle, which allows for the temporary existence of particles in a vacuum. This interplay means that the fabric of the cosmos was knitted together by processes affected by quantum mechanics. Additionally, the concept of cosmic inflation, a rapid expansion of the universe just after the Big Bang, is steeped in quantum physics. Inflationary theory posits that tiny quantum fluctuations could have been stretched to macroscopic scales during this exponential growth, seeding the universe's structure. This suggests that our understanding of the universe's evolution is not complete without incorporating quantum mechanics into our cosmological models. Moreover, the quest to unify gravity, which governs large-scale cosmic phenomena, with quantum mechanics, which defines the microcosm, remains one of the most significant challenges in physics today. Various theories, including string theory and loop quantum gravity, aim to bridge these two realms. A successful unification could lead to a deeper understanding of phenomena such as black holes and the mysterious nature of dark matter and dark energy, ultimately reshaping our comprehension of the universe itself. Quantum computing stands on the edge of revolutionizing our understanding of the universe by harnessing the peculiar principles of quantum mechanics. Unlike classical computers, which process information in bits as either a 0 or a 1, quantum computers utilize quantum bits, or qubits. These qubits can exist in multiple states simultaneously thanks to a phenomenon known as superposition. This ability allows quantum machines to perform complex calculations at speeds unimaginable with our current technology. One of the most exciting implications of quantum computing lies in its potential to simulate quantum systems. The universe, at a fundamental level, operates under quantum mechanics, which means that many natural phenomena, from the behavior of elementary particles to the interactions in complex materials, may be challenging to model using traditional computational methods. Quantum computers could effectively simulate these interactions, offering insights into the properties of matter, chemical reactions, and even the formation of galaxies. Moreover, quantum computing could significantly enhance our ability to solve intricate problems in fields such as cosmology and particle physics. By analyzing vast datasets generated from experiments, such as those conducted at particle accelerators, quantum computers could identify patterns and relationships that would otherwise remain hidden. This capability could advance our understanding of dark matter and dark energy, two of the universe's most elusive components that account for the majority of its mass energy content. As quantum computing continues to develop, it holds the promise of transforming our exploration of the cosmos. By unlocking the mysteries of quantum mechanics, we may deepen our understanding of fundamental forces and properties that govern the universe. This technological innovation represents a bold leap into new realms of inquiry, pushing the limits of human knowledge and perhaps even leading us to answers about the origins of existence itself. The universe operates on a principle of balance, where forces and matter exist in a delicate equilibrium. This interplay is evident in the cycles of celestial bodies, the fusion processes in stars, and the gravitational pulls between planets. Understanding these cosmic balances gives us profound insights into how we can cultivate sustainability on Earth. Just as celestial bodies orbit and interact in harmony, our approaches to environmental stewardship must also embrace interconnectedness and balance. Our planet's ecosystems serve as a microcosm of universal dynamics. For instance, the carbon cycle, where carbon is exchanged among the atmosphere, oceans, and living organisms, mirrors the cycles observed in space. Everything is linked, and the lessons of balance from cosmic interactions can teach us about maintaining these essential cycles on Earth. If we over-extract resources or disrupt habitats, we risk tipping the balance, leading to consequences that can ripple across entire ecosystems, much like the disastrous effects caused by the gravitational disruption of a celestial body. Additionally, the concept of resilience in the universe applies directly to our sustainability efforts. Stars evolve and explode in supernovae, enriching the universe with elements necessary for life, while planetary systems develop mechanisms to support varied forms of life. Inspired by these processes, we can cultivate resilience in our urban and agricultural environments, allowing them to adapt and thrive amid changing conditions. This means fostering biodiversity, practicing regenerative agriculture, and investing in renewable energies that reflect the continuity we observe on a cosmic scale. Ultimately, applying the universe's balance means embracing a holistic perspective. This approach encourages us to understand not only the individual components of our environment, but also how these elements interrelate. Whether it is through conservation efforts or innovative technologies, we can work towards a sustainable future that acknowledges our place within a larger cosmic symphony. By learning from the balance of the universe, we can create a more harmonious relationship with our planet, ensuring its health for generations to come. In recent years, the emphasis on sustainable living has inspired a wave of scientific innovations aimed at addressing the pressing challenges posed by climate change and resource depletion. One of the most exciting developments is the advancement of renewable energy technologies. Solar panels have become more efficient, with new designs allowing them to capture sunlight in less than ideal conditions, maximizing energy production. Wind turbines have also evolved, with larger blades and improved aerodynamics, leading to greater energy generation capabilities, even in lower wind speeds. Another significant innovation is the rise of sustainable agriculture practices, particularly vertical farming. This method utilizes multi-story buildings to grow crops in a controlled environment, reducing the land and water needed for traditional farming. By employing hydroponics and aeroponics, farmers can cultivate fresh produce year-round, minimizing the carbon footprint associated with food transport. These systems can use up to 90% less water than conventional methods, showcasing their potential to promote both sustainability and food security. Urban areas are also seeing innovative approaches to sustainability, notably through the integration of smart city technologies. These systems harness data and sensors to optimize energy consumption, improve waste management, and enhance public transportation efficiency. For instance, smart grids can dynamically manage energy distribution based on demand while decreasing reliance on fossil fuels. Additionally, some cities are implementing green roofs and walls, which not only improve insulation and reduce energy usage, but also contribute to urban biodiversity and reduce the urban heat island effect. Moreover, innovations in material science are changing the landscape of sustainability. Biodegradable plastics made from natural sources and advances in recycling technologies are making it possible to reduce waste significantly. These materials can break down more easily in the environment, curbing plastic pollution and its harmful effects on ecosystems. As we continue to develop and adopt these innovative technologies, the journey towards sustainable living becomes not just a possibility, but an achievable reality. Understanding Earth's ecosystems is integral to combating climate change because these complex networks play a vital role in regulating the planet's climate. Ecosystems can be thought of as the Earth's natural support systems, consisting of interactions between living organisms and their physical environment. By studying these interconnected relationships, scientists can identify how changes in climate affect biodiversity and, conversely, how healthy ecosystems can mitigate climate impacts. Forests, for example, are significant carbon sinks. They absorb carbon dioxide from the atmosphere and store it within trees, plants, and soil. When we understand the dynamics of forest ecosystems, we can take informed action such as reforestation and sustainable forest management. These strategies help enhance carbon storage capability, ensuring ecosystems continue to absorb greenhouse gases rather than releasing them, which is crucial as the Earth experiences rising temperatures and more frequent extreme weather events. Wetlands also contribute dramatically to carbon sequestration while providing flood protection and water filtration. Recognizing the role these ecosystems play helps drive efforts to conserve and restore them, which in turn shallows the impact of climate change. Every ecosystem, from oceans to grasslands, contributes uniquely to this puzzle, and understanding their roles enables better conservation and restoration strategies that are essential in our fight against climate change. Finally, ecosystems provide invaluable services to humanity, including food security, clean water, and health benefits. A well-functioning ecosystem can enhance our resilience to climate change by providing these services more effectively. As we face the challenges posed by climate change, harmonizing our interaction with natural environments becomes not only beneficial, but a necessity for our survival on this planet. Renewable energy technologies are poised to play a monumental role in shaping our future on Earth. As we face the pressing challenges of climate change and dwindling fossil fuel resources, these technologies offer a sustainable alternative that promises not just to reduce greenhouse gas emissions, but also to foster energy independence and economic growth. Wind, solar, Hydroelectric and geothermal power sources are at the forefront of this transition, each harnessing the planet's natural resources in a way that minimizes environmental impact. Solar energy, in particular, has seen a dramatic expansion in recent years. With advancements in photovoltaic cell efficiency and battery storage, solar power can now be generated even in less than ideal conditions, providing clean electricity to homes and businesses alike. Similarly, wind energy has transformed landscapes, with farms of turbines generating significant energy while also providing local jobs and stimulating economies. These technologies not only produce energy, but also catalyze innovation in energy storage and grid management, paving the way for a more resilient energy infrastructure. Moreover, the role of renewable energy technologies extends beyond just power generation. They encourage a shift in how we view energy consumption, promoting efficiency and sustainable practices. By integrating renewable sources into our energy mix, we can create an environment where local communities take an active role in their energy needs, from residential solar installations to community wind projects. This decentralization of energy production diminishes reliance on large, polluting power plants, ultimately leading to cleaner air and healthier populations. The future will also see increased investment in research and development of renewable energy systems. Governments and businesses worldwide are recognizing that innovation in this sector is critical, not only for environmental preservation, but also for economic stability. As technology continues to progress, we can look forward to a world where renewable energy is not merely an alternative, but the primary source of power, propelling us toward a sustainable and prosperous future on our planet. Conservation efforts play a vital role in sustaining the Earth's natural resources, creating a balance that benefits both the environment and humanity. At the core of these efforts is the principle of responsible management, which aims to ensure that resources such as water, forests, and wildlife are used sustainably. This means that we can enjoy the benefits of these resources today without jeopardizing their availability for future generations. For instance, preserving biodiversity through conservation projects ensures the resilience of ecosystems. Healthy ecosystems provide essential services like clean air and water, pollination of crops, and regulation of climate. When we protect habitats from encroachment and pollution, we not only safeguard wildlife, but also maintain the intricate web of life that supports human existence. The decline of any species can have ripple effects throughout the ecosystem, making conservation a key factor in maintaining overall environmental health. Furthermore, conservation strategies often advocate for the restoration of degraded areas. Reforestation, for example, focuses on planting new trees where forests have been depleted. This not only helps restore the habitat, but also contributes to carbon capture, playing an important role in mitigating climate change. By investing in these rehabilitative measures, we are actively working to replenish the planet's resources, promoting a cycle of renewal that benefits all forms of life. In addition, conservation efforts frequently engage the community. Involving local populations in managing natural resources helps empower these communities and teaches sustainable practices. These grassroots initiatives often result in more effective stewardship of the environment as people who rely on these resources become invested in their preservation. As we look toward the future, aligning conservation with resource management will be crucial for ensuring a healthy planet and a thriving human population. Throughout history, cultures across the globe have looked to the cosmos with a sense of wonder, using the stars, planets, and natural phenomena to weave stories that reflect their beliefs, values, and understanding of the world. In ancient times, celestial bodies were often seen as divine entities, powerful beings that influenced the behavior of humans and the events on Earth. For instance, the Egyptians revered the sun god Ra, while the Greeks personified the planets in the myths of their gods and goddesses. Such interpretations provided a divine framework for explaining not only the mysteries of the universe, but also the human experience. As societies evolved, so did the understanding of the cosmos. The advent of scientific inquiry during the Renaissance marked a significant shift in how people perceived the heavens. Figures like Nicholas Copernicus proposed that the Earth revolved around the Sun, challenging long-held beliefs. This heliocentric model ignited debates that led to the scientific revolution, fundamentally altering humanity's place in the universe. The cosmos transformed from a realm of myth and mysticism into a subject of rigorous study, shifting interpretations from the divine to the empirical. In more recent centuries, advancements in technology have further deepened our connection and understanding of the cosmos. Telescopes expanded our view, revealing distant galaxies and offering glimpses into the origins of the universe itself. Theories such as the Big Bang have provided a scientific narrative that explains the cosmos's beginnings, merging cultural narratives with observable evidence. This blending of science and cultural interpretation has allowed us to appreciate the universe not only as a physical entity, but as a backdrop for human existence. Today, cultural interpretations of the cosmos continue to evolve alongside scientific understanding. As we explore the potential for life beyond Earth, the fascination with astrobiology and the search for extraterrestrial intelligence has entered popular discourse. Modern storytelling, including films, literature, and art, reflects these themes, fueling our imaginations and inviting us to ponder our place within this vast universe. The cosmos, once a mystical domain, now serves as a canvas on which humanity paints its hopes, fears, and aspirations for the future. Throughout history, significant astronomical discoveries have profoundly influenced human culture in various ways. When we first turned our gaze to the stars, ancient civilizations began to shape their destinies around celestial events. The rise of agriculture, for instance, was closely linked to the movements of the sun and the moon, as farmers relied on these celestial markers to predict seasonal changes. As societies evolved, the night sky became a canvas for myth-making, with constellations serving not just as navigational aids, but also as rich sources of stories that explained our existence. The advent of powerful telescopes in the early 17th century, particularly the work of Galileo Galilei, marked a transformative shift in our understanding of the cosmos. This pivotal moment not only expanded our knowledge, but also challenged long-standing beliefs. The revelation that the Earth was not the center of the universe shattered the geocentric worldview and paved the way for modern science. The implications of this discovery extended beyond astronomy, fostering a spirit of inquiry that fueled the Enlightenment and ultimately influenced art, philosophy, and religion. In the contemporary era, astronomical discoveries continue to shape our cultural landscape. The exploration of the solar system and the discovery of exoplanets have ignited imaginations about the possibility of life beyond Earth. This curiosity has permeated literature, film, and art, inspiring entire genres that reflect our dreams and fears about the unknown. Popular culture, from sci-fi movies to television shows, frequently weaves in astronomical themes, encouraging a fascination with the universe and our place within it. Furthermore, as we venture into deeper space, our discoveries prompt philosophical reflections on existence and humanity's role in the universe. The Hubble Space Telescope, for example, has provided breathtaking images that reveal not only the beauty of the cosmos, but also our own insignificance in the grand scale of the universe. Such realizations have led to a renewed sense of wonder and responsibility towards our planet and beyond, reminding us that as we seek to understand the stars, we must also cherish and protect the home we inhabit. Cultural perspectives play a significant role in shaping scientific inquiry and interpretation. Every scientist operates within a specific social and cultural context that can influence their questions, methods, and the interpretations they make from their findings. For example, certain cultures may prioritize specific scientific issues over others, leading researchers to focus on problems that are most relevant to their communities. This can affect everything from environmental research to health sciences. Moreover, the values and beliefs inherent in a culture can shape the way scientific results are perceived and accepted. In some instances, findings that contradict widely held cultural beliefs may face skepticism or rejection. This phenomenon can be observed in various areas, such as climate change, where cultural attitudes significantly impact public acceptance and policymaking. The ongoing dialogue between science and culture is essential for fostering understanding and advancing knowledge. On the flip side, incorporating diverse cultural perspectives can enrich scientific inquiry. Different worldviews can challenge prevailing assumptions and open new avenues for research. This is particularly evident in fields such as ethnobiology, where traditional knowledge contributes valuable insights into biodiversity and ecosystem management. When scientists collaborate with indigenous populations, they often uncover information that traditional scientific methods might overlook. Finally, it's crucial to recognize the global nature of science today. Collaborative projects that span multiple cultures and regions often lead to more innovative solutions to complex problems. Such frameworks encourage the exchange of ideas, perspectives, and methodologies, ultimately strengthening the scientific process. As we move forward, embracing this cultural diversity will not only enhance scientific inquiry, but also ensure that the interpretation of scientific knowledge is more inclusive and reflective of our shared humanity. Space exploration has profoundly influenced art and literature, intertwining the realms of science and creativity in captivating ways. As humanity has reached for the stars, artists and writers have often sought to reflect the wonder, fear, and excitement that accompany our quest to understand the universe. The imagery of space, the vastness of the cosmos, planets with unusual landscapes, and distant galaxies becomes a backdrop for exploring complex themes like existence, identity, and the future of humanity. From the early days of rocketry, authors like H.G. Wells and Jules Verne envisioned journeys to the moon and beyond, pushing the boundaries of imagination at a time when such travels seemed purely fantastical. Their works laid the foundation for a genre that would grow exponentially as real space missions brought the wonders of the universe into sharper focus. Novels such as Arthur C. Clarke's 2001, A Space Odyssey, not only prophesied technological advances, but also prompted discussions about artificial intelligence and the nature of consciousness, ideas that are becoming more relevant as our technological capabilities evolve. Visual art has also reaped the rewards of space exploration. Artists like Chesley Bonestell redefined astronomical illustrations in the 1950s, bringing to life images of Saturn's rings and Martian landscapes. These depictions inspired generations of dreamers and scientists alike, shaping public perception of space and sparking interest in scientific inquiry. Today, contemporary artists harness data from space missions, translating scientific discoveries into visual forms that resonate with both art enthusiasts and the scientifically curious. In recent years, as trips to space become more accessible, both literature and art have embraced themes of personal exploration and the human connection to the cosmos. Works inspired by actual astronaut experiences or the technological marvels of space shuttles reveal an emotional and philosophical dimension to our ventures beyond Earth. This ongoing dialogue between the realms of science and the arts fosters a deeper appreciation for the ever-expanding universe, reminding us that exploration is not only about reaching new frontiers, but also about capturing the profound questions of existence that such journeys inspire. As we gaze into the vastness of the universe, we encounter a tapestry woven with unsolved mysteries that tantalize scientists around the globe. One of the most compelling enigmas is dark matter. Although it constitutes about 27% of the universe's mass energy content, we cannot directly observe dark matter. Its presence is inferred through gravitational effects on visible matter, such as galaxies. The search for its true nature and identity has led to numerous theories, including the possibility of exotic particles that interact very weakly with regular matter. Another mystery lies within dark energy, a force believed to be responsible for the accelerated expansion of the universe. This mysterious energy makes up approximately 70% of the universe, yet its composition is unfathomable to us. Its existence raises profound questions about the ultimate fate of the universe. Is it destined for eternal expansion, or will it eventually halt and reverse? Understanding dark energy remains one of the most significant challenges for modern cosmologists. The nature of black holes also generates tremendous fascination. These incredibly dense regions in space warp everything around them, even light, yet the physics that governs them is still not fully understood. The recent discovery of gravitational waves, ripples in spacetime caused by colliding black holes, has opened a new frontier in our comprehension of these cosmic giants. As we probe deeper into their behavior, questions arise about phenomena such as singularities and the event horizon, pushing our understanding of physics to its limits. Lastly, the existence of alien life is a mystery that captivates not just scientists, but humanity as a whole. The vastness of the cosmos makes it difficult to believe we are alone. Despite decades of searching and countless discoveries of exoplanets, we have yet to find definitive evidence of extraterrestrial life. Each planet we discover in the habitable zone raises more questions than answers. Are we on the verge of discovering life beyond Earth, or are we mere observers in an empty universe? The quest to uncover the truth behind these mysteries continues, driving explorers and scientists to push the boundaries of what we know about our universe. As we gaze into the universe, countless frontiers in exploration beckon us to uncover new cosmic phenomena. Among these, the advancement of next-generation telescopes stands out as a cornerstone of modern astronomy. Instruments like the James Webb Space Telescope are already transforming our understanding of the cosmos. Designed to observe infrared light, Webb can peer deeper into space and further back in time than ever before, uncovering distant exoplanets, ancient galaxies, and the building blocks of stars and planets. This capability holds the potential to reveal phenomena we have yet to imagine, including insights into the origins of the universe itself. Another exciting frontier lies in gravitational wave astronomy. The detection of gravitational waves, ripples in spacetime produced by cataclysmic events like black hole mergers, has opened a new avenue for observing the universe. Upcoming observatories, such as the European Space Agency's LISA, aim to detect low-frequency gravitational waves. This technology can provide a unique understanding of massive cosmic events and offer insights into the mysterious properties of black holes, neutron stars, and even the very fabric of the universe. The implications of this exploration are profound, as it may challenge our current theories in astrophysics. Moreover, explorations of the solar system's outer reaches are poised to reveal unprecedented discoveries. Missions like the ongoing exploration of Mars and the multifaceted study of the moons of Jupiter and Saturn are rapidly expanding our knowledge of these celestial bodies. For example, the recently launched Europa Clipper mission aims to evaluate the habitability of Jupiter's icy moon Europa by investigating its subsurface ocean. Discovering potential signs of life in these alien oceans represents a monumental leap in our quest to understand life's existence beyond Earth. Finally, the study of dark matter and dark energy continues to unveil a vast, largely invisible structure of the cosmos. Powerful new surveys and particle physics experiments are being launched to hunt for direct evidence of dark matter particles. Understanding these elusive entities could illuminate the nature of the universe's expansion and help bridge gaps in our current scientific models. These frontiers in exploration promise not only to reshape our knowledge of the universe, but also to ignite our imagination about the celestial wonders yet to be discovered. As we look ahead, the potential for future scientific breakthroughs to reshape our understanding of life and the universe is immense. Advances in fields like genetics, artificial intelligence, and quantum physics could open new doors to unraveling some of the most profound mysteries of existence. Imagine a future where we can decode the intricacies of life at a molecular level, potentially leading to revolutionary insights about what defines living organisms and how they interact with the universe. One area with significant promise is biotechnology. As we enhance our ability to edit genes and manipulate biological systems, we may discover entirely new forms of life, or at least redefine the boundaries of what life is. For instance, synthetic biology could lead us to create organisms that thrive in extreme environments, prompting us to reconsider the conditions required for life. This exploration may not only expand our understanding of life on Earth, but could also inform the search for extraterrestrial life in environments previously thought to be uninhabitable. Moreover, advancements in our understanding of consciousness and intelligence could redefine not only humanity's place in the cosmos, but also our relationship with technology. With the development of advanced artificial intelligence, we might soon engage with non-biological forms of consciousness. This could challenge our definitions of sentience and intelligence, compelling us to ask provocative questions about the nature of consciousness itself and whether it can exist independently from biological substrates. Finally, developments in astrophysics, particularly in the study of dark matter and dark energy, could radically alter our understanding of the cosmos. If we continue to probe the fundamental forces shaping our universe, we may find connections between the microscopic world and the vastness of space. Such discoveries would not only enlighten our comprehension of cosmic forces, but might also illuminate the origin of life and our ultimate place within this vast, enigmatic expanse. The future of scientific exploration holds tantalizing possibilities, each promising to expand the tapestry of knowledge about life and the universe in ways we can only begin to imagine. The search for life beyond our planet raises countless intriguing questions that elicit both wonder and curiosity. One of the most pressing inquiries is whether life can exist in environments vastly different from Earth. For instance, scientists are keen to explore whether life might thrive in the thick clouds of Venus, where sulfuric acid and extreme pressure create extraordinarily hostile conditions. Alternatively, moons like Europa and Enceladus, with their subsurface oceans, provoke questions about the types of organisms that might be living under their icy crusts. Another fascinating topic involves the potential for intelligent life elsewhere in the universe. If advanced civilizations exist, will we ever make contact with them? Researchers ponder how extraterrestrial beings might communicate and whether they possess technologies that could rival our own. The famed Fermi paradox highlights this tension. Given the vast number of stars and potentially habitable planets, why have we not yet encountered signs of intelligent life? Additionally, understanding the building blocks of life serves as a cornerstone for these inquiries. Scientists are investigating how organic molecules, which serve as the foundation for life as we know it, are formed in space, and whether they can seed life on planets with the right conditions. Astrobiologists are particularly excited about the prospect of discovering extremophiles, organisms that can survive in harsh environments on Earth, because they offer clues about how life might survive in similar conditions elsewhere. As technology advances, our ability to explore these questions deepens. Missions to Mars and the far moons of our solar system are unfolding before our eyes, while powerful telescopes search the skies for exoplanets in the habitable zone of distant stars. Each new discovery not only brings us closer to answering these questions, but also opens up even more possibilities. The mystery of life beyond Earth continues to intrigue scientists and enthusiasts alike, leaving us eager for the discoveries that lie ahead. Human activity has propelled our exploration and understanding of the universe in profound ways, sparking a desire to ask questions and seek answers that extend far beyond the horizon of our everyday experiences. From the ancient civilizations that gazed at the stars, to modern space agencies launching sophisticated spacecraft, our innate curiosity has driven remarkable advancements in our quest to comprehend the cosmos. One of the most significant milestones in this journey was the invention of the telescope in the early 17th century. This groundbreaking device allowed astronomers to observe celestial bodies in unprecedented detail. Figures like Galileo and Copernicus fundamentally altered our understanding of the universe, shifting our perspective from an Earth-centered to a Sun-centered system. These early discoveries laid the foundation for modern astronomy, establishing a trajectory for exploration that would only accelerate with time. As technology evolved, so did our methods of exploring the universe. The launch of the first artificial satellite, Sputnik, in 1957 marked the beginning of space exploration. This was soon followed by human spaceflight and the Apollo missions that landed humans on the Moon. Each of these achievements expanded our scientific knowledge, provided insights into the complexities of our own planet, and revealed the beauty and mysteries of our solar system. In recent decades, the establishment of space telescopes like the Hubble and missions that traveled to distant planets, asteroids, and even comets have enhanced our understanding even further. These instruments have become our eyes in the sky, enabling us to study phenomena billions of light years away. Coupled with advancements in computer technology, data analysis, and international collaboration, humanity's exploration of the universe has transformed from mere observation to a deeper understanding of cosmic history, unfolding the mysteries of dark matter, black holes, and the very nature of existence itself. Through all of this, human activity has not only advanced our knowledge of the universe, but it has also reminded us of our place within it, igniting a shared sense of wonder and curiosity that continues to drive our exploration forward. Humanity's venture into space is not just a quest to understand the cosmos, it also sheds light on how we can better protect our own planet. The challenges faced in space exploration often revolve around sustainability, resource management, and environmental impact. As we send missions beyond Earth, we are forced to confront the limitations of our resources and the fragility of our ecological systems. This reflection prompts important lessons about how to safeguard Earth's ecosystems. One of the key insights from space exploration comes from the study of life support systems used in spacecraft. These systems recycle air, water, and waste materials, showcasing innovative methods that could be adapted for use on Earth. For instance, the closed-loop water systems on the International Space Station demonstrate the potential for reducing water waste in arid regions on our planet. By applying these technologies, we can establish more efficient tools for conserving vital resources back on Earth. Moreover, observing our planet from space provides a unique perspective on environmental changes. Satellites monitor deforestation, climate shifts, and pollution levels, enabling scientists and policymakers to respond more effectively to these issues. This panoramic view of Earth allows us to grasp the interconnectedness of different ecosystems and the human impacts on them. Thus, the very act of observing Earth from afar highlights the urgency of addressing our environmental crises. Finally, the spirit of cooperation inherent in space agencies around the world acts as a model for global collaboration on Earth. Just as countries come together to share knowledge and resources for interplanetary missions, so too must they unite to tackle planetary problems like climate change and biodiversity loss. Humanity's exploration of the cosmos thus not only broadens our scientific horizons, but also reinforces the importance of stewardship for our home planet. Human curiosity is a powerful driving force that propels us to explore the universe. From the moment we gain consciousness, we are innately drawn to ask questions about our existence and the world around us. This quest for understanding has led to monumental advancements in various fields, especially cosmology, where we seek to unravel the origins, structure, and potential fates of the universe itself. At its core, curiosity sparks innovation. Early humans turned to the stars for navigation, which not only guided them across vast oceans, but also paved the way for metaphysical inquiries about what lies beyond. Ancient civilizations observed celestial patterns, creating myths and early astronomical practices. These primitive questions set the stage for modern science, transforming speculation into rigorous methods of inquiry that underpin our exploration of the cosmos today. The quest for knowledge has continually expanded our horizons. With the invention of telescopes in the 17th century, humanity began to peer deeper into the universe, revealing marvels like planets beyond our own and vast galaxies scattered across the night sky. Each discovery ignited new questions, highlighting that our understanding is always evolving. More recently, developments in technology allow us to capture cosmic events, such as the merging of black holes or the formation of distant stars, helping to piece together the universe's intricate puzzle. Ultimately, human curiosity drives us to seek answers beyond our world. It compels scientists to devise theories, create experiments, and ask the profound questions that matter most. As we continue to challenge our understanding and explore the unknown, we are not merely charting the cosmos, we are also learning about ourselves. The grand quest to unravel the universe's mysteries is, at its heart, a quest to grasp the very essence of what it means to be human. Private companies are poised to play a transformative role in the future of space exploration, forging new pathways and expanding the frontiers of our cosmic ambitions. Historically, space exploration was largely the domain of governmental agencies such as NASA and the European Space Agency. However, as technological advancements have progressed and public interest in space has surged, private enterprises have emerged as key players in this arena, bringing a blend of innovation, efficiency, and fresh investment. At the forefront of this movement are companies like SpaceX, Blue Origin, and Virgin Galactic. These enterprises have developed rockets and spacecraft that can launch payloads into orbit at significantly lower costs than traditional government-run programs. SpaceX's Falcon rockets and Crew Dragon spacecraft have already demonstrated this capability, notably with missions that transport astronauts to and from the International Space Station. This shift towards commercial capabilities not only democratizes access to space, but also paves the way for new business models, including space tourism, satellite deployment, and potentially even asteroid mining. Moreover, private companies are fostering collaboration with government space agencies to achieve ambitious goals like lunar exploration and crewed missions to Mars. NASA has partnered with several private firms through initiatives like the Commercial Crew Program. This collaboration allows for shared expertise and resources, speeding up development timelines and leading to a more sustainable exploration strategy. The blending of public and private efforts means that missions once considered the domain of only governmental entities can now be tackled with the agility and creativity that private firms bring to the table. Looking ahead, as these companies continue to innovate, the possibilities seem endless. We could witness an era where commercial colonies on the Moon or Mars become reality, bolstered by advances in technology and a new economic framework for space activities. The involvement of private enterprises catalyzes a new space age, inspiring a fresh generation of scientists, engineers, and explorers to look towards the stars, expand our understanding of the universe, and perhaps even find new homes beyond Earth. Throughout history, ancient civilizations gazed up at the night sky with a mixture of wonder and curiosity. They were not just stargazers. They were keen observers who saw patterns in the cosmos that greatly informed their understanding of the world. Cultures across the globe, from the Mayans in Central America to the Greeks in the Mediterranean, crafted intricate celestial maps, attributing meaning to the constellations and planetary movements. By tracking these celestial bodies, they designed calendars that guided agricultural cycles, religious festivals, and social governance. For example, the ancient Egyptians connected their complex mythology to the stars. They aligned their monumental pyramids with specific stars, believing that these celestial bodies played a vital role in the afterlife. They worshipped gods linked to different aspects of the heavens, and their elaborate ritualistic practices were directly influenced by celestial phenomena. This connection between the cosmos and daily life highlights how ancient peoples perceived their existence as part of a larger, interconnected universe. Similarly, the Babylonians made significant advancements in astronomy, creating one of the first known star catalogues. They understood that the movements of planets, which they called wandering stars, followed specific cycles, leading to the development of astrology. an ancient practice that sought insight into human affairs based on celestial events. These early astronomical insights laid the groundwork for modern astronomy, and some of their observational techniques are still relevant in contemporary studies. The legacies of these ancient interpretations live on in various ways today. Modern astronomy continues to rely on the groundwork laid by these cultures, and their understanding of the cosmos sparks our own scientific explorations. Furthermore, the myths and stories created around stars and planets have influenced literature, art, and even navigational techniques throughout the centuries. As we extend our gaze into the universe with modern telescopes and space missions, we carry forward the curiosity and reverence of those ancient civilizations, reminding us that the stars have always been a source of inspiration and inquiry. Throughout history, humans have sought to understand the cosmos, resulting in several groundbreaking theories that laid the foundation for modern science. One of the earliest models came from the ancient Greeks, particularly from the philosopher Aristotle in the 4th century BCE. Aristotle proposed a geocentric view, suggesting that the Earth was the center of the universe, with the stars and planets revolving around it. This model dominated for centuries and influenced medieval thought despite its inaccuracies. In the 2nd century CE, the astronomer Claudius Ptolemy refined Aristotle's ideas into a comprehensive system known as the Ptolemaic model. His work, the Almagest, introduced epicycles, which were small circular orbits that explained the apparent retrograde motion of planets. For more than 1400 years, this geocentric model prevailed, forming the backbone of astronomical study in Europe and the Islamic world, even as European explorers began to observe the heavens more closely. The Renaissance marked a significant shift in cosmology, primarily driven by figures like Nicholas Copernicus. In the 16th century, Copernicus boldly proposed a heliocentric model, asserting that the Sun, not Earth, was at the center of the universe. This revolutionary idea eventually unraveled the long-held Ptolemaic views, leading to increased observational scrutiny and paving the way for future scientists like Johannes Kepler and Galileo Galilei, who would further develop and support the heliocentric theory with their astronomical observations. Understanding these historical theories sheds light on humanity's enduring quest to comprehend the universe. Each of these paradigms, though flawed by modern standards, represented significant advancements in thought, highlighting our evolving understanding of place within the cosmos. As we marvel at today's discoveries, it is crucial to appreciate the intellectual journey that brought us from ancient views to our current understanding of the universe as we explore the cosmos with tools like telescopes and satellites. Throughout history, lunar and solar events like eclipses and the phases of the moon have profoundly influenced global cultures and scientific understanding. Ancient civilizations, such as the Babylonians and Egyptians, meticulously observed these celestial phenomena, leading them to develop early forms of calendars based on lunar cycles. The regularity of these events not only fascinated them, but also played a pivotal role in agricultural practices, guiding planting and harvesting times by aligning them with the changing moon. Eclipses, in particular, have held significant cultural meanings across various societies. For the ancient Greeks, solar eclipses were seen as omens. The philosopher Anaxagoras famously proposed that the moon was simply a rock reflecting sunlight, which challenged the prevailing beliefs of his time and laid the groundwork for future astronomical inquiry. In different cultures, eclipses have been interpreted as battles between celestial entities, reflecting humanity's desire to understand and find meaning in the cosmos. On the scientific front, the study of lunar and solar events has led to major advancements in our understanding of the universe. Observing eclipses has allowed astronomers like Sir Arthur Eddington during the early 20th century to confirm Albert Einstein's theory of general relativity by measuring how starlight bends around the sun. These observations turned simple celestial events into powerful tools that expanded our grasp of gravity and the fabric of space-time itself. In modern times, lunar and solar events continue to spark curiosity and inspire technological advancements. Events such as solar eclipses are live-streamed worldwide, educating millions about astronomy. The efforts to study lunar phases contribute to vital scientific data related to tides and ecosystems on Earth. Ultimately, these celestial events weave through the history of human thought, influencing our cultures, guiding our scientific journeys, and fostering a deeper appreciation for the universe in which we reside. Throughout history, certain key figures have profoundly influenced our understanding of the universe, transforming the way we perceive our place in the cosmos. One of the earliest revolutionaries was the ancient Greek philosopher Aristotle, who proposed a geocentric model, placing Earth at the center of the universe. This theory dominated for centuries, shaping not only scientific thought, but also cultural perspectives on humanity's position in the cosmos. The transition to a heliocentric model, with the Sun at the center, marked a significant turning point, largely credited to the work of Nicholas Copernicus. His groundbreaking ideas, presented in the 16th century, challenged the long-standing beliefs of Aristotle and the Church. This shift was further advanced by the meticulous observations of Tycho Brahe and the brilliant mathematical formulation of Johannes Kepler, who revealed the elliptical orbits of planets. Kepler's laws of planetary motion not only refined the heliocentric theory, but also laid the groundwork for future exploration into gravitational forces. In the 17th century, Sir Isaac Newton expanded our understanding with his laws of motion and universal gravitation. Newton's work created a unifying framework that explained not only the motion of celestial bodies, but also terrestrial phenomena. His ability to quantify gravitational attraction fundamentally changed our approach to cosmology, leading to the realization that the same forces that govern the movement of falling apples also govern the celestial spheres. Fast forward to the 20th century, and we encounter Albert Einstein, whose theories of relativity revolutionized our comprehension of space and time. Einstein's famous equation revealed the profound connection between mass and energy, while his general theory of relativity illustrated how gravity is the warping of space-time by mass. This opened new avenues in the study of cosmological phenomena, such as black holes and the expansion of the universe, propelling humanity toward an ever-deepening understanding of the vast and intricate cosmos that surrounds us. Each of these historical figures has not merely added knowledge, they have reshaped our worldview, inspiring multiple generations to look up at the stars and contemplate the mysteries of the universe. Modern technologies have revolutionized the study of astronomy and space in ways that were once unimaginable. In the past, astronomers relied mainly on the naked eye, along with basic telescopes to make their observations. Today, advanced instruments like space-based telescopes, high-powered ground observatories, and sophisticated software have opened up a vast universe of possibilities. These technologies allow scientists to explore the cosmos with remarkable precision and clarity, unveiling celestial phenomena that were hidden from view for centuries. One of the most significant advancements is the development of space telescopes, like the Hubble Space Telescope, which has provided breathtaking images of distant galaxies and nebulae. Freed from the distortions of the Earth's atmosphere, space telescopes have dramatically improved our ability to observe the universe across various wavelengths of light. For instance, infrared telescopes enable us to glimpse cooler celestial objects, such as star-forming regions obscured by dust, while X-ray observatories reveal high-energy events, such as black hole accretion and supernova explosions. In addition to telescopes, modern technology has fostered the growth of computational astrophysics, where data analysis and simulations enhance our understanding of cosmic events. Researchers utilize powerful supercomputers to simulate the formation of galaxies, the dynamics of planetary systems, and the behavior of dark matter. The vast amounts of data these simulations generate are analyzed using advanced algorithms, helping scientists make connections and form predictions about the universe's structure and evolution. Moreover, space exploration has taken remarkable strides with missions such as the Mars rovers and Voyager spacecraft. These missions equip us with unparalleled hands-on data and insights about other planets and celestial bodies. As technologies continue to evolve, the future of astronomy shines brightly, promising new discoveries that may fundamentally change our comprehension of the universe, our place within it, and even the possible existence of extraterrestrial life. As we embrace these advancements, the cosmos remains a tantalizing frontier, waiting to share its secrets. As we gaze toward the horizon of technological development, several innovations stand poised to revolutionize our understanding of both life and the universe. One remarkable area is the advancement of artificial intelligence and machine learning, which hold the potential to decode vast amounts of astronomical and biological data. With the capability to analyze patterns and make connections that may elude human researchers, these technologies can help unveil the mysteries of galaxies, the formation of stars, and even the complexity of life itself. Quantum computing represents another frontier that could dramatically shift our grasp of cosmology and biology. By harnessing the power of quantum mechanics, these computers can perform calculations at speeds unimaginable with current technology. This extraordinary speed could allow scientists to simulate complex systems such as the formation of molecular structures or cosmic events with unprecedented accuracy. The insights gained from these simulations could reshape our understanding of how life originated and evolved on Earth, and potentially reveal signs of life beyond our planet. Moreover, advancements in space exploration technology, such as more efficient propulsion systems and deeper space telescopes, can extend our reach into the cosmos. These tools enable us to observe distant exoplanets and gather data on their atmospheres, increasing the chances of discovering signs of habitability or even extraterrestrial life. As we explore our neighboring planets in the solar system, missions to Mars or the moons of Jupiter and Saturn could yield surprising findings on life's potential to thrive in diverse environments. Lastly, biotechnology continues to progress at a breathtaking pace. Techniques like CRISPR gene editing are already transforming our understanding of biology by allowing precise alterations in DNA. This technology not only sheds light on the fundamental principles of life, but also opens possibilities for biotechnology applications in space travel, such as creating resilient crops for long missions, or even altering human biology to endure the harsh conditions of space. Altogether, these technological advancements will likely revolutionize our comprehension of life on Earth and throughout the cosmos, leading us toward new frontiers of knowledge and exploration.